Chapter 31 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Jason Humphreys. Astronomy, the Science of the Heavenly Bodies by David Todd. The Solar Corona. "And what is the sun's corona?" mildly asked a college professor of a student who might better have answered, "Not prepared." "I did know, Professor, but I have forgotten," was his reply. "What an incalculable loss to science," returned the professor with a twinkle. "The only man who ever knew what the sun's corona is, and he has forgotten." Only in part has the mystery of the corona been cleared by the research of the present day. Our knowledge proceeds but slowly because the corona has never been seen except during total eclipses of the sun, and astronomers, as a matter of fact, have never had a fair chance at it. 2 total eclipses happen on the average of every 3 years. Their average duration is only 2 or 3 minutes. Totality can be seen only in a narrow path about 100 miles wide, though it may be several thousand miles long. There is usually about equal chance of cloud with clear skies, and fully 3/4 of the totality areas of the globe are unavailable because covered by water. So that even if we imagine the tracks of eclipses quite thickly populated with astronomers and telescopes, at least one every 100 miles, how much solid watching of the corona would this permit? Only little more than 1 week's time in a whole century. The true corona is at least a triple phenomenon, and a very complex one. The photographs reveal it much as the eye sees it, with all its complexity of interlacing streamers projected into a flat, or plane, surrounding the disk of the dark moon, which hides the true sun completely. But we must keep in mind the fact that the sun is a globe, not a disk, and that the streamers of the corona radiate more or less from all parts of the surface of the solar sphere, much as quills from a porcupine. From the sun's magnetic poles branch out the polar rays, nearly straight throughout their visible extent. Gradually, as the coronal rays originate at points around the solar disk, farther and farther removed from the poles, they are more and more curved. Very probably they extend into the equatorial regions, but it is not easy to trace them there because they are projected upon and confused with the filaments having their origin remote from the poles. Then there is the inner equatorial corona, apparently connected intimately with truly solar phenomena, quite as the polar rays are. The third element in the composite is the outer ecliptic corona, for the most part made up of long streamers. This is most fully developed at the time of the fewest spots on the sun. It is traceable much farther against the black sky with the naked eye than by photography. Without any doubt, it is a solar appendage, and possibly it may merge into the zodiacal light. Naturally, this superb spectacle must have been an amazing sight to the beholders of antiquity who were fortunate enough to see it. Historical references are rare. Perhaps the earliest was by Plutarch about AD 100, who wrote of it, "A radiance shone round the rim, and would not suffer darkness to become deep and intense." Philostratus, a century later, mentions the death of the Emperor Domitian at Ephesus as announced by a total eclipse. Kepler thought the corona was evidence of a lunar atmosphere. Indeed, it was not until the middle of the 19th century that its lack of relation to the moon was finally demonstrated. Later observers, Wyberd in 1652 and Ulloa, got the impression that the corona turned round the disk Catherine wheel fashion, like an ignited wheel in fireworks turning on its center. But no later observer has reported anything of the sort. Quite the contrary. There it stands against a black sky in motionless magnificence, a colorless, pearly mass of wisps and streamers for the most part nebulous and ill-defined, fading out very irregularly into the black sky beyond, but with a complex interlacing of filaments, sometimes very sharply defined near the solar poles. It defies the skill of artist and draftsman to sketch it before it is gone. Photograph it? Yes, but there are troubles. Of course, the camera work is superior to sketches by hand. As Langley used to say, the camera has no nerves, and what it sets down we may rely on. Foremost among the photographic difficulties is the wide variation in intensity of the coronal light in different regions of the corona. If a plate is exposed long enough to get the outer corona, the exceeding brightness of the inner corona overexposes and burns out that part of the plate or film. If the exposure is short, we get certain regions of the inner corona excellently, but the outer regions are a blank because they can be caught only by a long exposure. So the only way is to take a series of pictures with a wide range of exposures, and then by careful and artistic handiwork combine them all into a single drawing. Wesley of London has succeeded eminently in work of this character, and his drawings of the sun's corona, visible at total eclipses from 1871 onward, in possession of the Royal Astronomical Society, are the finest in existence. They give a vastly better idea of the corona as the eye sees it than any single photograph possibly can. The early observers apparently never thought of the corona as being connected with the sun. It was a halo merely, and so drawn. Its real structure was neither known, depicted, or investigated. Sketches were structureless, as any aureola formed by stray sunlight grazing the moon might naturally be. That the rays are curved and far from radial around the sun was shown for the first time in the sketches of 1842. And in 1860 Sir Francis Galton observed that the long arms or streamers do not radiate strictly from the center. The inner corona had first been recorded photographically on a daguerreotype plate during the eclipse of 1851, but the lens belonged to a heliometer and was, of course, uncorrected for the photographic rays. The wet collodion plates of the eclipse of 1860 by de la Rue proved that not only the prominences but the corona were truly solar, because his series of technically perfect pictures revealed the steady and unchanged character of these phenomena while the moon's disk was passing over them as totality progressed. And at the eclipse of 1869, Young put the solar theory of the corona beyond the shadow of any further doubt by examination of its light with the spectroscope, and discovering a green line in the spectrum due to incandescent vapor of a substance not then identified with anything terrestrial, and therefore called coronium. The total brilliance of the corona was very differently estimated by the earlier observers, though pretty carefully measured at later eclipses. The standard full moon is used for reference, and at one eclipse the corona falls short of, while at another it will exceed the full moon in brightness. Variations in brilliancy are quite marked. At one eclipse it was nearly 4 times as bright as the full moon. Much evidence has already accumulated on this question, but whether the observed variations are real, or due mainly to the varying relative sizes of sun and moon at different eclipses is not yet known. The coronal light is largely bluish in tint, and this is the region of the spectrum most powerfully absorbed by our atmosphere. Eclipses are observed by different expeditions located at stations where the eclipsed sun stands at very different altitudes above the horizon. Besides this, the localities of observation are at varied elevations above sea level, so that the varying amount of absorption of the coronal light renders the problem one of much difficulty. The long ecliptic streamers of the corona were first seen by Newcomb and Langley during the totality of 1878. On one side of the sun there was a stupendous extension of at least 12 solar diameters, or nearly 11 millions of miles. Langley observed from the summit of Pikes Peak, over 14,000 feet high, and was sure that he was witnessing a real phenomenon heretofore undescribed. The vast advantage of elevation was apparent also from the fact that he held the corona for more than 4 minutes after true totality had ended. These streamers are characteristic of the epoch of minimum spots on the sun, as Ranyard first suggested. It was found that this type of corona had been recorded also in 1867, and it has reappeared in 1889, 1900, and 1911, and will doubtless be visible again in 1922. How rapidly the streamers of the corona vary is not known. Occasionally an observer reports having seen the filaments vibrate rapidly, as in the aurora borealis, but this is not verified by others who saw the same corona perfectly unmoving. Comparisons of photographs taken at widely separate stations during the same eclipse have shown that at least the corona remained stationary for hours at a time. Whether it may be unchanged at the end of a day, or a week, or a month is not known, because no two total eclipses can ever happen nearer each other than within an interval of 173 days, or 1/2 of the eclipse year. And usually the interval between total eclipses is twice or 3 times this period. Theories of what the solar corona may be are very numerous. The extreme inner corona is perhaps in part a sort of gaseous atmosphere of the Sun, due to matter ejected from the Sun and kept in motion by forces of ejection, gravity, and repulsion of some sort. Meteoric matter is likely concerned in it, and Huygens suggested the debris of disintegrating comets. Schuster was in agreement with Huygens that the brighter filaments of the corona might be due to electric discharges, but it seems very unlikely that any single hypothesis can completely account for the intricate tracery of so complex a phenomenon. Elaborate spectroscopic programs have been carried out at recent eclipses, affording evidence that certain regions are due to incandescent matter of lower temperature than the Sun's surface. A small part of the light of the corona is sunlight reflected from dark particles, possibly meteoric, but more likely dust particles or fog of some sort. This accounts for the weakened solar spectrum with Fraunhofer absorption lines, and this part of the light is polarized. Many have been the attempts to see or photograph the corona without an eclipse. None of them has, however, succeeded as yet. Huygens got very promising results nearly 40 years ago, and success was thought to have been reached. But subsequent experiments on the Riffelberg in 1884 and later convinced him that his results related only to a spurious corona. In 1887, the writer made an unsuccessful attempt to visualize the corona from the summit of Fujiyama, and Hale tried both optical and photographic methods on Pikes Peak in 1893 without success. He devised later a promising method by which the heat of the corona in different regions can be measured by the bolometer, and an outline corona afterwards sketched from these results. Still another method of attacking the problem occurred to the writer in 1919, which has not yet been carried out. It would take advantage of recent advances in aeronautics, and contemplates an artificial eclipse in the upper air by means of a black spherical balloon. This would be sent up to an altitude of perhaps 40,000 feet, where it would partake of the motion of the air current in which it came to equilibrium. Then a snapshot camera would be mounted on an aeroplane in which the aviator would ascend to such a height that the balloon just covered the Sun, as the Moon does in a total eclipse. With the center of the balloon in line with the Sun's center, he would photograph the regions of the sky immediately surrounding the Sun, against which the corona is projected. As the entire apparatus would be above more than an entire half of the Earth's atmosphere, the experiment would be well worth the attempt, as pretty much everything else has been tried and found wanting. Needless to say, the importance of seeing the corona at regular intervals whenever desired, without waiting for eclipses of the Sun, remains as insistent as ever. End of Chapter 31.
Chapter 32 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Rick Vina. Astronomy, the Science of the Heavenly Bodies, by David Todd. The Ruddy Planet. Mars is a planet next in order beyond the Earth, and its distance from the Sun averages 141.5 million miles. It has a relatively rapid motion among the stars. Its color is reddish, and, when nearest to us, it is perhaps the most conspicuous object in the sky. Mars appeared to the ancients just as it does to us today. Aristotle recorded an observation of Mars, 356 BC, when the moon passed over the planet, or occulted it, as our expression is. Galileo made the first observations of Mars with a telescope in 1610, and his little instrument was powerful enough to enable him to discover that the planet had phases, though it did not pass through all the phases that Mercury and Venus do. This was obvious from the fact that Mars is always at a greater distance from the Sun than we are, and the phase can only be gibbous, or about like the Moon, when midway between full and quarter. Many observers in the 17th century followed up the planet with such feeble optical power as the telescopes of that epoch provided. Fontana, who made the first sketch, Riccioli and Bianchini in Italy, Cassini in France, Huygens in Holland, and later Sir William Herschel in England. It was Cassini who first made out the whitish spots or polar caps of Mars in 1666, but not until after Huygens had noted the fact that Mars turned around on an axis in a period but little longer than the Earth's. Cassini followed it up later with a more accurate value, and observations in our own day, when combined with these early ones, enable us to say that the Martian day is equal to 24 hours, 37 minutes, 22.67 seconds, accurate probably to the 100th part of a second. When we know that a planet turns round on an axis, we know that it has a day. When we know the direction of the axis in space, or in relation to the plane of its path round the Sun, we know that it has seasons. We can tell their length and when they begin and end. It did not take many years of observation to prove that the axis round which Mars turns is tilted to the plane of its path round the Sun by an angle practically the same as that at which the Earth's axis is tilted. So, there is the immediate inference that on Mars the order and perhaps the character of the seasons is much the same as here on the Earth. At least two things, however, tend to modify them. First, the year of Mars is not 365 days like ours, but 687 days. Each of the 4 seasons on Mars, therefore, is proportionally longer than our seasons are. Then comes the question of atmosphere. How much of an atmosphere does Mars really possess in proportion to ours, and how would its lesser amount modify the blending of the seasons into one another? All discussion of Mars and the problems of existence of life upon that planet hinge upon the character and extent of Martian atmosphere. The planet seems never to be covered, as the Earth usually is, with extensive areas of cloud, which to an observer in space would completely mask its oceans and continents. Nearly all the time, Mars, in his equatorial and temperate zones, is quite clear of clouds. A few whitish spots are occasionally seen to change their form and position in both northern and southern latitudes, and they vary with the progress of the day on Mars, as clouds naturally would. But Schiaparelli, perhaps the best of all observers, thought them to be not low-lying clouds of the nimbus type that would produce rains, but rather a veil of fog, or perhaps a temporary condensation of vapor, as dew or hoar frost. But the strongest argument for an atmosphere is based on the temporary darkening or obscuration of well-known and permanent markings on the surface of Mars. These are more or less frequently observed, and clouds afford the best explanation of their occurrence. So much for evidence supplied by the telescope alone. When, however, we employ the spectroscope in conjunction with the telescope, another sort of evidence is at hand. Several astronomers have reached the conclusion that watery vapor exists in the atmosphere of Mars, while other astronomers, equipped with equal or superior apparatus and under equally favorable or even better conditions, have reached the remarkable conclusion that the spectra of Mars and the Moon are identical in every particular. From this, we should be led to infer that Mars has perhaps no more atmosphere than the Moon has, that is to say, none whatever that present instruments and methods of investigation have enabled us to detect. What, then, shall we conclude? Simply that the atmosphere of Mars is neither very dense nor extensive. Probably its lower strata close to the planet's surface are about as dense as the Earth's atmosphere is at the summits of our highest mountains. This conclusion is not unwelcome if we keep a few fundamental facts in clear and constant view. Mars is a planet of intermediate size between the Earth and the Moon. Twice the Moon's diameter, 2,160 miles, very nearly equals the diameter of Mars, 4,200 miles, and twice the diameter of Mars does not greatly exceed the Earth's diameter, 7,920 miles. As to the weights or masses of these bodies, Mars is about 1/9, and the Moon 1/80 of the Earth. The atmospheric envelope of the Earth is abundant. The Moon has none, as far as we can ascertain. So it seems safe to infer that Mars has an atmosphere of slight density, not dense enough to be detected by spectroscopic methods, but yet dense enough to enable us to explain the varying telescopic phenomena of the planet's disk, which we should not know how to account for if there were no atmosphere whatever. One astronomer has indeed gone so far as to calculate that in comparison with our planet, Mars is entitled to 1/20 as much atmosphere as we have, and that the mercurial barometer at sea level would run about 5½ inches, as against 30 inches on the Earth. In general, then, the climate of Mars is probably very much like that of a clear season on a very high terrestrial tableland or mountain, a climate of wide extremes, with great changes of temperature from day to night. The inequality of Martian seasons is such that in his northern hemisphere the winter lasts 381 days and the summer only 306 days. Now, the polar caps of Mars, which are reasonably assumed to be due to snow or hoar frost, attain their maximum 3 or 4 months after the winter solstice, and their minimum about the same length of time after the summer solstice. This lagging should be interpreted as an argument for a Martian atmosphere with heat-storing qualities, similar to that possessed by the Earth. Upon this characteristic indeed depends the climate at the surface of Mars, whether it is at all similar to our own, and whether fluid water is a possibility on Mars or not. While the cosmic relations of the planet in its orbit are quite the same as ours, nevertheless, the greater distance of Mars diminishes his supply of direct solar heat to about half what we receive. On the other hand, his distance from the sun during his year of motion around it varies much more widely than ours, so that he receives when nearest the sun about 1/2 more of solar heat than he does when farthest away. Southern summers on Mars, therefore, must be much hotter, and southern winters colder than the corresponding seasons of his northern hemisphere. Indeed, the length of the southern summer, nearly twice that of the terrestrial season, sometimes amply suffices to melt all the polar ice and snow, as in October 1894, when the southern polar cap of Mars dwindled rapidly and finally vanished completely. Very interesting in this connection are the researches of Stoney on the general conditions affecting planetary atmospheres and their composition. According to the kinetic theory, if the molecules of gases which are continually in motion travel outward from the center of a planet, as they frequently must, and with velocities surpassing the limit that a planet's gravity is capable of controlling, these molecules will effect a permanent escape from the planet and travel through space in orbits of their own. So the moon is wholly without atmosphere, because the moon's gravity is not powerful enough to retain the molecules of its component gases. So also, the Earth's atmosphere contains no helium or free hydrogen. So, too, Mars is possessed of insufficient force of gravity to retain water vapor, and the Martian atmosphere may therefore consist mainly of nitrogen, argon, and carbon dioxide. As everyone knows, the axis of the Earth, if extended to the northern heavens, would pass very near the North Polar Star, which on that account is known as Polaris. In a similar manner, the axis of Mars pierces the northern heavens about midway between the two bright stars Alpha Cephei and Alpha Cygni, Deneb. The direction of this axis is pretty accurately known because the measurement of the polar caps of the planet as they turn round from night to night, year in and year out, has enabled astronomers to assign the inclination of the axis with great precision. These caps are a brilliant white, and they are generally supposed to be snow and ice. They wax and wane alternately with the seasons on Mars, being largest at the end of the Martian winter and smallest near the end of summer. The existence of the polar caps, together with their seasonal fluctuations, afford a most convincing argument for the reality of a Martian atmosphere, sufficiently dense to be capable of diffusing and transporting vapor. The northern cap is centered on the pole almost with geometric exactness and as far as the 85th parallel of latitude. On the other hand, the south polar cap is centered about 200 miles from the true pole, and this distance has been observed to vary from one season to another. No suggestion has been made to account for this singular variation. On one occasion, it stretched down to Martian latitude 70 degrees and was over 1,200 miles in diameter. Pickering watched the changing conditions of shrinking of the south polar cap in 1892 with a large telescope located in the Andes of Peru. Mars was faithfully followed on every night but one, from July 13 to September 9, and the apparent alterations in this cap were very marked, even from night to night. As the snows began to decrease, a long, dark line made its appearance near the middle of the cap, and gradually grew until it cut the cap in two. This white polar area, and probably also the northern one in similar fashion, becomes notched on the edge with the progress of its summer season. Dark interior spots and fissures form. Isolated patches separate from the principal mass and later seem to dissolve and disappear. Possibly, if one were located on Mars and viewing our Earth with a big telescope, the seasonal variation of our north and south polar caps might present somewhat similar phenomena. All the recent oppositions of Mars have been critically observed by Pickering from an excellent station in Jamaica. Quite obviously, the fluctuations of the polar caps are the key to the physiographic situation on Mars, and they are made the subject of the closest scrutiny at every recurring opposition of the planet. Several observers, Lowell in particular, record a bluish line, or a sort of retreating polar sea, following up the diminishing polar cap as it shrinks with the advance of summer. It is said that no such line is visible during the formation of the polar cap with the approach of winter. all such results of critical observation, just on the limit of visibility, have to be repeated over and over again before they become part of the body of accepted scientific fact. And in many instances, the only sure way is to fall back on the photographic record, which all astronomers, whether prejudiced or not, may have the opportunity to examine and draw their individual conclusions. Already, the approaching opposition of 1924, the most favorable since the invention of the telescope, is beginning to attract attention, and preparations are in progress of new and more powerful instruments with new and more sensitive photographic processes, by means of which many of the present riddles of Mars may be solved. End of chapter 32.
Chapter 33 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Read by Piotr Natter. The Astronomy, the Science of the Heavenly Bodies, by David Todd. The Canals of Mars. Then there are the so-called Canals of Mars, about which so much is written and relatively little known. Faint markings which resemble them in character were first drawn in 1840 and later in 1864, but Schiaparelli, the famous Italian astronomer, is probably their original discoverer, when Mars was at its least distance from the Earth in 1877. He made the first accurate detailed map of Mars at this time, and most of the important or more conspicuous canals, canali he called them in Italian, that is, channels merely, without any reference whatever to their being watercourses, were accurately charted by him. At all the subsequent close approaches of Mars, the canals have been critically studied by a wide range of astronomical observers, and their conclusions as to the nature and visibility of the canals have been equally wide and varied. The most favourable oppositions have occurred in 1892 and 1894, also in 1907 and 1909. On these occasions a close minimum distance of Mars was reached, that is, about 35 millions of miles. But in 1924 the planet makes the closest approach in a period of nearly 1,000 years. Its distance will not much exceed 34 millions of miles. But although this is a minimum distance for Mars, it must not be forgotten that it is a really vast distance, absolutely speaking. It is something like 150 times greater than the distance of the Moon. With no telescopic power at our command, could we possibly see anything on the Moon of the size of the largest buildings or other works of human intelligence, so that we seem forever barred from detecting anything of the sort on Mars? Nevertheless, the closest scrutiny of the ruddy planet by observers of great enthusiasm and intelligence, coupled with imagination and persistence, have built up a system of canals on Mars, covering the surface of the planet like spider webs over a printed page, crossing each other at intersecting spots known as lakes, and embodying a wealth of detail which challenges criticism and explanation. To see the canals at all requires a favourable presentation of Mars, a steady atmosphere and a perfect telescope, with a trained eye behind it. Not even then are they sure to be visible. The training of the eye has no doubt much to do with it, so photography has been called in, and very excellent pictures of Mars have already been taken, some nearly half as large as a dime, showing plainly the lights and shades of the grander divisions of the Martian surface, but only in a few instances revealing the actual canals more unmistakably than they are seen at the eyepiece. The appearance and degree of visibility of the canals are variable. Possibly clouds temporarily obscure them, but there is a certain capriciousness about their visibility that is little understood. In consequence of the changing physical aspects as to season on Mars and his orbital position with reference to the Earth, some of the canals remain for a long time invisible, adding to the intricacy of the puzzle. For the most part the canals are straight in their course and do not swerve much from a great circle on the planet, but their lengths are very different, some as short as 250 miles, some as long as 4,000 miles, and they often join one another like spokes in a hub of a wheel, though at various angles. As depicted by Lowell and his corps of observers at Flagstaff, Arizona, the canal system is a truly marvellous network of fine darkish stripes. Their colour is represented as a bluish green. Each marking maintains its own breadth throughout its entire length, but the breadth of all the canals is by no means the same. The narrowest are perhaps 15 to 20 miles wide, and the broadest probably 10 times that. At least that must be the breadth of the Nilocertes, which is generally regarded as the most conspicuous of all the canals. The lower observatory has outstripped all others in the number of canals seen and charted, now about 500. What may be the true significance of this remarkable system of markings it is impossible to conclude at present. Schiaparelli, from his long and critical study of them, their changes of width and colour, was led to think that they may be a veritable hydrographic system for distributing the liquid from the melting polar snows. In this case it would be difficult to escape the conviction that the canals have, at least in part, been designed and executed with a definite end in view. Lowell went even farther and built upon their behaviour an elaborate theory of life on the planet, with intelligent beings constructing and opening new canals on Mars at the present epoch. Pickering propounded the theory that the canals are not water-bearing channels at all, but that they are due to vegetation starting in the spring when first seen, and vitalized by the progress of the season poleward, the intensity of colour of the vegetation coinciding with the progress of the season as we observe it. Extensive irrigation schemes for conducting agricultural operations on a large scale seem a very plausible explanation of the canals, especially if we regard Mars as a world farther advanced in its world history than our own. Erosion may have worn the continents down to their minimum elevation, rendering artificial waterways not difficult to build, while with the vanishing Martian atmosphere and absence of rains, the necessity of water for the support of animal and vegetal life could only be met by conducting it in artificial channels from one region of the planet to another. Interesting as this speculative interpretation is, however, we cannot pass by the fact that many competent astronomers, with excellent instruments finely located, have been unable to see the canals, and therefore think the astronomers who do see them are deceived in some way. Also many other astronomers, perhaps on insufficient grounds, deny their existence in toto. Many patient years of labour would be required to consult all the literature of investigation of the planet Mars, but much of the detail has been critically embodied in maps at different epochs, by Kaiser, Proctor, Green and Dreyer, and Flammarion, in 2 classic volumes on Mars, has presented all the observations from the earliest time, together with his own interpretation of them. Areography is a term sometimes applied to a description of the surface of Mars, and it is scarcely an exaggeration to say that areography is now better known than the geography of immense tracts of the earth. For some reason well recognized, though not at all well understood, Mars, although the nearest of all the planets, Venus alone excepted, is an object by no means easy to observe with the telescope. Possibly its unusual tint has something to do with it. With an ordinary opera glass examine the moon very closely, and try to settle precise markings, colours, and the nature of objects on her surface. Mars, under the best conditions, scrutinized with our largest and best telescope, presents a problem of about the same order of difficulty. There are delicate and changing local colours that add much uncertainty. Nevertheless, the planet's leading features are well made out, and their stability since the time of the earliest observers leaves no room to doubt their reality as parts of the permanent planetary crust. The border of the Martian disc is brighter than the interior, but this brightness is far from uniform. Variations in the colour of the markings often depend on the planet's turning round on its axis, and the relation of the surface to our angle of vision. If we keep in mind these obstacles to perfect vision in our own day, It is easy to see why the early users of the very imperfect telescopes failed to see very much, and were misled by much that they thought they saw. Then, too, they had to contend, as we do, with unsteadiness of atmosphere, which is least troublesome near the zenith. As their telescopes were all located in the northern hemisphere, the northern hemisphere of Mars is the one best circumstanced for their investigation, because at the remote oppositions of Mars, which always happen in our northern winter, with the planet in high north declination, it is always the north pole of Mars which is presented to our view, whereas the close oppositions of the planet always come in our northern midsummer, with Mars in south declination, and therefore passing through the zenith of places in corresponding south latitude. With Mars near opposition, high up from the horizon, a fairly steady atmosphere, and a magnifying power of at least 200 diameters, even the most casual observer could not fail to notice the striking difference in brightness of the two hemispheres, the northern chiefly bright and the southern markedly dark. Formerly this was thought to indicate that the southern hemisphere of Mars was chiefly water, and the northern land, much as is the case on the earth, with this difference, however, that water and land on the earth are proportioned about as 11:4, but Mars in its general topography presents no analogy with the present relation of land and water on the earth. There seems no reason to doubt that the northern regions, with their prevailing orange tint, in some places a dark red, and in others fading to yellow and white, are really continental in character. Other vast regions of the Martian surface are possibly marshy, the varying depth of water causing the diversity of colour. If we could ever catch a reflection of sunlight from any part of the surface of Mars, we might conclude that deep water exists on the planet. But the farther research progresses, the more complete becomes the evidence that permanent water areas on Mars, if they exist at all, are extremely limited. Since 1877 Mars has been known to possess two satellites, which were discovered in August of that year by Hall at Washington. Moons of this planet had long been suspected to exist, and on one or two previous occasions critically looked for, though without success. In the writings of Dean Swift there is a fanciful allusion to the two moons of Mars, and if astronomers had chanced to give serious attention to this, Phobos and Deimos, as Hall named them, might have been discovered long before. They are very small bodies, not only faint in the telescope, but actually of only 10 or 20 miles diameter, and from the strange relation that Phobos, the inner moon, moves round Mars 3 times, while the planet itself is turning round only once on its axis, some astronomers incline to the hypothesis that this moon at least was never part of Mars itself, but that it was originally an inner or very eccentric member of the asteroid group, which ventured within the sphere of gravitation of Mars, was captured by that planet, and has ever since been tributary to it as a secondary body or satellite. End of chapter 33.
Chapter 34 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Light Crystal. Astronomy, the Science of the Heavenly Bodies, by David Todd. Life in Other Worlds. Popular interest in astronomy is exceedingly wide, but it is very largely confined to the idea of resemblances and differences between our Earth and the bodies of the sky. The question most frequently asked the astronomer is, have any of the stars got people on them? Or more specifically, is Mars inhabited? The average questioner will not readily be turned off with yes or no for an answer. He may or may not know that it is quite impossible for astronomers to ascertain anything definite in this matter. Most interesting as it is, what he wants to find out is the view of the individual astronomer on this absorbing and ever-recurring inquiry. We ought first to understand what is meant by the manifestation here on the earth called life, and agree concerning the conditions that render it possible. Apparently they are very simple. We may or may not agree, that a counterpart of life, or life of a wholly different type from ours, may exist on other planets under conditions wholly diverse from those recognized as essential to its existence here. The problem of the origin of life is, in the present state of knowledge, highly speculative and hardly within the domain of science. Here on Earth, life is intimately associated with certain chemical compounds, in which carbon is the most common element without which life would not exist. Also hydrogen, oxygen, and nitrogen are present, with iron, sulfur, phosphorus, magnesium, and a few less important elements besides. But carbon is the only substance absolutely essential. Protoplasm cannot be built without it, and protoplasm makes up the most of the living cell. Closely related to carbon is silica also. As a substitution in certain organic compounds, protoplasm is able to stand very low temperatures, but its properties as a living cell cease when the temperature reaches 150 Fahrenheit. Animal life, as it exists on the Earth today, appears to have been here many million years. The paleontologists agree that all life originated in the waters of the Earth. It has passed through evolutionary stages, from the lowest to the highest. Throughout this vast period, the astronomer is able to say that the conditions of the Earth, which appear to be essential to the maintenance of life, have been pretty constantly what they are today. The higher the type of life, the narrower the range of conditions under which it thrives. Man can exist at the frigid poles, even if the temperature is 75 degrees below Fahrenheit 0, and in the deserts and the tropics. He swelters under temperatures of 115 degrees, but he still lives. At these extremes, however, he can scarcely be said to thrive. We have, then, a relatively narrow range of temperatures which seems to be essential to his comfortable existence and development. We may call it 150 degrees in extent. Had not the surface temperature of the Earth been maintained within this range for indefinite ages, in the regions where the human race has developed, quite certainly man would not be here. How this equability of temperature has been maintained does not now matter. Clearly the Earth must have existed through indefinite ages in the process of cooling down from temperatures of at least 6,000 degrees. During this stage, the temperature of the surface was Earth-controlled. Then this period merged very gradually into the stage where life became possible, and the temperature of the surface became, as it now is, sun-controlled. How many years are embraced in this span of periods, or ages, we have no means of knowing, but of the sequence of periods and the secular diminution of temperature we may be certain. Then there is the equally important consideration of water necessary for the origination, support, and development of life. We cannot conceive of life existing without it. On the Earth, water is superabundant, and has been for indefinite ages in the past. There is little evidence that the oceans are drying up, although the commonly accepted view is that the waters of the Earth will very gradually disappear. Water can exist in the fluid state, which is essential to life, at all temperatures between 32 degrees and 680 degrees Fahrenheit. Air to breathe is essential to life also. The atmosphere which envelopes the Earth is at least 100 miles in depth, and its own weight compresses it to a tension of nearly 15 pounds to the square inch at sea level. This atmosphere and its physical properties have had everything to do with the development of animal life on the planet. Without it, and its remarkable property of selective absorption, which imprisons and diffuses the solar heat, it is inconceivable that the necessary equability of surface temperature could be maintained. This appears to be quite independent of the chemical constituents of the atmosphere, and is perhaps the most important single consideration affecting the existence of life on a planet. If the surface of a planet is partly covered with water, it will possess also an atmosphere containing aqueous vapour. Heat, water, and air. These three essentials determine whether there is life on a planet or not. Of course, there must be nutrition suitable to the organism, mineral for the vegetal, and vegetal for the animal. But the narrow range of variation appears to be the striking thing. Relatively but a few degrees of temperature and a narrow margin of atmospheric pressure. If this pressure is doubled or trebled, as in submarine caissons, life becomes insupportable. If, on the other hand, it is reduced even 1/3, as on mountains even 13,000 feet high, the human mechanism fails to function, partly from lack of oxygen necessary in vitalizing the blood, but mainly because of simple reduction of mechanical pressure. If, then, we conceive of life in other worlds, and it is agreed that life there must manifest itself much as it does here, our answer to the question of habitability of the planets must follow upon an investigation of what we know, or can reasonably surmise, about the surface temperatures of these bodies, whether they have water, and what are the probable physical characteristics of their atmospheres. We may inquire about each planet, then, concerning each of these details. The case of Mercury is not difficult. At an average distance of only 36 million miles from the Sun, and with a large eccentricity of orbit which brings it a fifth part nearer, conditions of temperature alone must be such as to forbid the existence of life. The solar heat received is 7 times greater than that at the Earth, and this is perhaps sufficient reason for a minimum of atmosphere, as indicated by observation. If no air, then quite certainly no water, as evaporation would supply a slight atmosphere. But according to the kinetic theory of gases, the mass of Mercury, only a very small fraction of that of the Sun, is inadequate to retain an atmospheric envelope. If, however, the planet's day and year are equal, so that it turns a constant face to the Sun, surface conditions would be greatly complicated, so that we cannot regard the planet as absolutely uninhabitable on the hemisphere that is always turned away from the Sun. Venus, at 67 millions of miles from the Sun, presents conditions that are quite different. She receives double the solar heat that we do, but possessing an atmosphere perhaps 3-fold denser than ours, as reliably indicated by observations of transits of Venus. The intensity of the heat and its diffusion may be greatly modified. What the selective absorption of the atmosphere of Venus may be, we do not know, nor is the rotation time of the planet definitely ascertained. If equal to her year, as many observations show, and as indicated by the theory of tidal evolution, there may well be certain regions on the hemisphere perpetually turned away from the Sun, where temperature conditions are identical with those on the tropical Earth, and where every condition for the origin and development of life is more fully met than anywhere else in the solar system. Whether Venus has water distributed as on the Earth, we do not know, as her surface is never seen, owing to dense clouds under which she is always enshrouded. Her cloudy condition possibly indicates an overplus of water. Is the Moon inhabited? Quite certainly not. No appreciable air, no water, and a surface temperature unmodified by atmosphere, rising perhaps to 100 degrees Fahrenheit during the day, which is a fortnight in length, and falling at night to 300 degrees below zero, if not lower. Is Mars inhabited? The probable surface temperature is much lower than the Earth's, because Mars receives only half as much solar heat as we do, and more important still, the atmosphere of Mars is neither so dense nor so extensive as our own. Seasons on Mars are established, much the same as here, except that they are nearly twice as long as ours, and alternate shrinking and enlarging of the polar caps keeps even pace with the seasons, thereby indicating a certainty of atmosphere whose equatorial and polar circulation transports the moisture poleward to form the snow and ice of which the polar caps no doubt consist. There is a variety of evidence pointing to an atmosphere on Mars of 1/3 to 1/2 the density of our own, an atmosphere in which free hydrogen could not exist, although other gases might. The spectroscopic evidence of water vapour in the Martian atmosphere is not very strong. It is very doubtful whether water exists on Mars in large bodies, quite certainly not as oceans, though the evidence of many small lakes is pretty well made out. With very little water, a thin atmosphere, and a zero temperature, is Mars likely to be inhabited at the present time? The chances are rather against it. If, however, the past development of the planet has progressed in the way usually considered as probable, we may be practically certain that Mars has been inhabited in the past, when water was more abundant and the atmosphere more dense, so as to retain and diffuse the solar heat. Biologists tell me that they hardly know enough regarding the extreme adaptability of organisms to environment to enable them to say whether life on such a planet as Mars would or would not keep on functioning with secular changes of moisture and temperature. The survival of a race might be ensured against extremely low temperatures by dwelling in sub-Martian caves, and sufficient water might be preserved by conceivable engineering and mechanical schemes. But the secular reduction of the quantity and pressure of atmosphere, it is not easy to see how a race even more advanced than ourselves could maintain itself alive under serious lack of an element so vital to existence. Both Wallace, the great biologist, and Arrhenius, the eminent chemist, but biologist, astronomer, and physicist as well, both reject the habitation theory of Mars, regarding the so-called canals as quite like the luminous streaks on the Moon, that is, cracks in the volcanic crust caused by internal strains due to the heated interior. Wallace, indeed, argues that the planet is absolutely uninhabitable. The asteroids, or minor planets? We may dismiss them with the simple consideration that their individual masses are so insignificant and their gravity so slight that no atmosphere can possibly surround them. Their temperatures must be exceedingly low, and water, if present at all, can only exist in the form of ice. Jupiter, the giant planet, presents the opposite extreme. His mass is nearly 1,000th part of the Sun's, and is sufficient to retain a very high temperature, probably approximating to the condition we call red hot. This precludes the possibility of life at the outset, although the indications of a very dense atmosphere many thousand miles in depth are unmistakable. Of Saturn, 1/3500th the mass of the Sun. Practically the same may be said. Proctor thought it quite likely that Saturn might be habitable for living creatures of some sort, but he regarded the planet as on many accounts unsuitable as a habitation for beings constituted like ourselves. Mere consideration of surface temperature precludes the possibility of life in the present stage of Saturn's development, but the consensus of opinion is to the effect that life may make its appearance on these great planets at some inconceivably remote epoch in the future, when the surface temperature is sufficiently reduced for life processes to begin. Discoveries of algae, flourishing in hot springs approaching 200 degrees Fahrenheit, make it possible that these beginnings may take place earlier and at much higher temperatures than have hitherto been thought possible. A century ago, when the ring of Saturn was believed to be a continuous plane, this was a favourite corner of the solar system for speculation as to habitability. But now that we know the true constitution of the rings, no one would for a moment consider any such possibility. Conditions may, however, be quite different with Saturn's huge satellite Titan, the giant moon of the solar system. Its diameter makes it approximately the size of the planet Mars, and although it is much further removed from the Sun, its relative nearness to the highly heated globe of Saturn may provide the equability of temperature which is essential to life processes. Also, the 3 inner Galilean moons of Jupiter, especially 3, which is about the size of Titan, are excellently placed for life possibilities as far as probable temperature is concerned. But we have of course no basis for surmising what their conditions may be as to air and water, except that their small mass would indicate a probable deficiency of those elements. Uranus and Neptune are planets so remote, and their apparent disks are so small, that very little is known about their physical condition. They are each about 1/3 the diameter of Jupiter, and the spectrum of Uranus shows broad diffused bands, indicating strong absorption by a dense atmosphere very different from that of the Earth. Indications are that Neptune has a similar atmosphere. It is possible that the denser atmospheres of these remote planets may be so conditioned as to selective absorption that the relatively slender supply of solar heat may be conserved, and thus ensure a relatively high surface temperature when the Sun comes into control. If our theories of origin of the planets are to be trusted, we may rather suppose that Uranus and Neptune are still in a highly heated condition, that life has not yet made its appearance on them, but that it will begin its development ages before Saturn and Jupiter have cooled to the requisite temperature. Comets. In his Lettres Cosmologiques, 1765, Lambert considers the question of habitability of the comets, naturally enough in his day, because he thought them solid bodies surrounded by atmosphere and related to the planets. The extremes of temperature at perihelia and aphelia to which the comets are subjected did not bother him particularly. After calculating that the comet of 1680, being 160 times nearer to the Sun than we are ourselves, must have been subjected to a degree of heat 25,600 times as great as we are, Lambert goes on to say, whether this comet was of a more compact substance than our globe, or was protected in some other way, it made its perihelion passage in safety, and we may suppose all its inhabitants also passed safely. No doubt they would have to be of a more vigorous temperament and of a constitution very different from our own. But why should all living beings necessarily be constituted like ourselves? Is it not more infinitely probable that amongst the different globes of the universe a variety of organizations exist, adapted to the wants of the people who inhabit them, and fitting them for the places in which they dwell, and the temperatures to which they will be subjected? Is man the only inhabitant of the earth itself? And if we had never seen an either bird or fish, should we not believe that the air and water were uninhabitable? Are we sure that fire has not its invisible inhabitants, whose bodies, made of asbestos, are impenetrable to flame? Let us admit that the nature of the beings who inhabit comets is unknown to us, but let us not deny their existence, and still less the possibility of it. Little enough is really known about the physical nature of comets even now, but what we do know indicates incessant transformation and instability of conditions that would render life of any type exceedingly difficult of maintenance. A word about Sir William Herschel's theory of the Sun and its habitability. He thought the core of the Sun a dark solid body, quite cold, and surrounded by a double layer, the inner one of which he conceived to act as a sort of fire screen to shield the Sun proper against the intense heat of the outer layer, or photosphere by which we see it. Viewed in this light, the Sun, he says, appears to be nothing else than a very eminent, large and lucid planet, evidently the first, or, in strictness of speaking, the only primary one of our system. It is most probably also inhabited, like the rest of the planets, by beings whose organs are adapted to the peculiar circumstances of that vast globe. But physics and biology were undeveloped sciences in Herschel's days. Herschel knew, however, that the stars are all suns, so that he must have conceived that they are inhabited also, quite independently of the question whether they possess retinues of planets after the manner of our solar system. This again is a question to which the astronomer of the present day can give no certain answer. So immensely distant are even the nearest of these multitudinous bodies that no telescope can ever be built large enough or powerful enough to reveal a dark planet as large as Jupiter, alongside even the nearest fixed star. Whatever may be the process of stellar evolution, there doubtless is an era of many hundreds of millions of years in the life of a star when it is passing through a planet-maintaining stage. This would likely depend upon spectral type, or to be indicated by it, and as about half of the stars are of the solar type, it would be a reasonable inference that at least half of the stars may have planets tributary to them. In such a case, the chances must be overwhelmingly in favour of vast numbers of the planets of other stellar systems being favourably circumstanced as to heat and moisture for the maintenance of life at the present time. That is, they are habitable, and if habitable, then thousands of them are no doubt inhabited now. But astronomers know absolutely nothing about this question, nor are they able to conceive at present any way that may lead them to any definite knowledge of it. There is, indeed, one piece of quasi-evidence which might reasonably be interpreted as implying that it is more likely that the stars are not attended by families of planets than that they are.
End of chapter 34.
Chapter 35 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Astronomy, the Science of the Heavenly Bodies, by David Todd. The Little Planets. Along toward the end of the 18th century and the beginning of the 19th, astronomers were leading a quiet, unexcited life. Sir William Herschel had been knighted by King George for his discovery of the outer planet Uranus, and practically everything seemed to be known and discovered in the solar system, with a single exception. Between Mars and Jupiter, there existed an obvious gap in the planetary brotherhood. Could it be possible that sometime in the remote cosmic past, a planet actually existed there, and that some celestial cataclysm had blown it to fragments? If so, would they still be traveling round the sun as individual small planets? And might it not be possible to discover some of them among the faint stars that make up the belt of the zodiac, in which all the other planets travel? So interesting was this question that the first International Association of Astronomers banded themselves together to carry on a systematic search round the entire zodiacal heavens in the faint hope of detecting possible fragments of the original planet of mere hypothesis. The astronomers of that day placed much reliance on what is known as Bode's law, not a law at all, but a mere arithmetical succession of numbers which represented very well the relative distances of all the planets from the sun. And the distance of the newly found Uranus fitted in so well with this law that the utter absence of a planet in the gap between Mars and Jupiter became very strongly marked. Quite by accident, a discovery of one of the Gestat small planetary bodies was made on January 1st, 1801, at Palermo, Sicily, by Piazzi, who was regularly occupied in making an extensive catalogue of the stars. His observations soon showed that the new object he had seen could not be a fixed star, because it moved from night to night among the stars. He concluded that it was a planet and named it Ceres, for the tutelary goddess of Sicily. Other astronomers kept up the search, and another companion planet, Pallas, was found in the following year. Juno was found in 1804, and Vesta, the largest and brightest of all the minor planets, in 1807. Vesta is sometimes bright enough when nearest the Earth to be seen with the naked eye, but it was the last of the brighter stars, and no more discoveries of the kind were made till the fifth was found in 1845. Since then, discoveries have been made in great abundance, more and more with every year, till the number of little planets at present known is very near 1,000. The early asteroid hunters found the search rather tedious, and the labor increased as it became necessary to examine the increasing thousands of fainter and fainter stars that must be observed in order to detect the undiscovered planets, which naturally grow fainter and fainter as the chase is prolonged. First, a chart of the ecliptic sky had to be prepared, containing all the stars that the telescope employed in the search would show. Some of the most detailed charts of the sky in existence were prepared in connection with this work, particularly by the late Dr. Peters of Hamilton College. Once such charts are complete, they are compared with the sky, night after night, when the moon is absent. Thousands upon thousands of tedious hours are spent in this comparison, with no result whatever, except that chart and sky are found to correspond exactly. But now and then the planet hunter is rewarded by finding a new object in the sky that does not appear on his chart. Almost certainly this is a small planet, and only a few nights' observation will be necessary to enable the discoverer to find out approximately the orbit it is traveling in, and whether it is out and out a new planet, or only one that had been previously recognized and then lost track of. Nearly all the minor planets so far found have had names assigned to them, principally legendary and mythological, and a nearly complete catalog of them, containing the elements of their orbits, that is, all the mathematical data that tells us about their distance from the Sun and the circumstances of their motion around him, is published each year in the Annuaire du Bureau des Longitudes at Paris. But these little planets require a great deal of care and attention, for some astronomers must accurately observe them every few years, and other astronomers must conduct intricate mathematical computations based on these observations. Otherwise, they get lost and have to be discovered all over again. Professor Watson of the University of Michigan and later of the University of Wisconsin endowed the 22 asteroids of his own discovery, leaving the National Academy of Sciences a fund for prosecuting this work perpetually, and Leuschner is now ably conducting it. While the number of the asteroids is gratifyingly large, their individual size is so small and their total mass so slight that even if there are 100,000 of them, as is wholly possible, they would not be comparable in magnitude with any one of the great planets. Vesta, the largest, is perhaps 400 miles in diameter, and if composed of substances similar to those which make up the Earth, its mass may be perhaps 1/20,000th of the Earth's mass. If we calculate the surface gravity on such a body, we find it about 1/13th of what it is here, so that a rifle ball, if fired on Vesta with a muzzle velocity of only 2,000 feet a second, might overmaster the gravity of the little planet entirely and be projected in space never to return. If, as is likely, some of the smallest asteroids are not more than 10 miles in diameter, their gravity must be so feeble a force that it might be overcome by a stone throw from the hand. There is no reliable evidence that any of the asteroids are surrounded by atmospheric gases of any sort. Probably they are, for the most part, spherical in form, although there is very reliable evidence that a few of the asteroids, being variable in the amount of sunlight that they reflect, are irregular in form, merely angular masses, perhaps. The network of orbits of the asteroids is inconceivably complicated. Nevertheless, there is a wide variation in their average distance from the Sun, as their periods of traveling round him vary in a similar manner, the shortest being only about 3 years, but the longest is nearly 9 years in duration. The average of all their periods is a little over 4 years. The gap in the zone of asteroids, at a distance from the Sun equal to about 5/8 that of Jupiter, is due to the excessive disturbing action of Jupiter, whose periodic time is just twice as long as that of a theoretical planet at this distance. The average inclination of their orbits to the plane of the ecliptic is not far from 8 degrees. But the orbit of Pallas, for example, is inclined 35 degrees, and the eccentricities of the asteroid orbits are equally erratic and excessive. Both eccentricity and inclination of orbit at times suggest a possible relation to cometary orbits, but nothing ever has been definitely made out connecting asteroids and comets in a related origin. No comprehensive theory of the origin of the asteroid group has yet been propounded that has met with universal acceptance. According to the nebular hypothesis, the original gaseous material, which should have been so concentrated as to form a planet of ordinary type, has, in the case of the asteroids, collected into a multitude of small masses instead of simply one. That there is a sound physical reason for this can hardly be denied. According to Laplacian hypothesis, the nearness of the huge planetary mass of Jupiter just beyond their orbits produced violent perturbations which caused the original ring of gaseous material to collect into fragmentary masses instead of one considerable planet. The theory of a century ago that an original great planet was shattered by internal explosive forces is no longer regarded as tenable. To astronomers engaged upon investigation of distances in the solar system, the asteroid group has proved very useful. The late Sir David Gill employed a number of them in a geometrical research for finding the Sun's distance, and more recently, the discovery of Eros has made it possible to apply a similar method for a like purpose when it approaches nearest to the Earth in 1924 and 1931. Then, the distance of Eros will be less than half that of Mars, or even Venus at their nearest. When the total number of asteroids discovered has reached 1,000, with accurate determination of all their orbits, we shall have sufficient material for a statistical investigation of the group which ought to elucidate the question of its origin, and bear on other problems of the cosmogony yet unsolved. Present methods of discovery of the asteroids by photography replace entirely the old method by visual observation alone, with the result that discoveries are made with relatively great ease and rapidity. End of section 35. Chapter 36 of Astronomy, the Science of Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Astronomy, the Science of the Heavenly Bodies, by David Todd. The Giant Planet. I can never forget as a young boy my first glimpse of the planet Jupiter and his moons. It was through a bit of a telescope that I had put together with my own hands, a tube of pasteboard, and a pair of old spectacle lenses that chanced to be lying about the house. In the field of view, I saw 5 objects, 4 of them looking quite alike, and as if they were stars merely. They were Jupiter's moons, while the 5th was vastly larger and brighter. It was circular in shape, and I thought I could see a faint darkish line across the middle of it. This experience encouraged me immensely, and I availed myself, eagerly of the first chance to see Jupiter through a bigger and better glass. Then I saw at once that I had observed nothing wrongly, but that I had seen only the merest fraction of what there was to see. In the first place, the planet's disk was not perfectly circular, but slightly oval. Inquiring into the cause of this, we must remember that Jupiter is actually not a flat disk, but a huge ball, or globe, more than 10 times the diameter of the Earth, which turns swiftly round on its axis once every 10 hours, as against the Earth's turning around in 24 hours. Then it is easy to see how the centrifugal force bulges outward the equatorial regions of Jupiter, so that the polar regions are correspondingly drawn inward, thereby making the polar diameter shorter than the equatorial one, which is in line with the moons or satellites. The difference between the two diameters is very marked, as much as 1 part in 15. All the planets are slightly flattened in this way, but Jupiter is the most so of all, except Saturn. The little darkish line across the planet's middle region or equator was found to be replaced by several such lines or irregular belts and spots, often seen highly colored, especially with reflecting telescopes, and they are perpetually changing their mutual relation and shapes because they are not solid territory or land on Jupiter, but merely the outer shapes of atmospheric strata blown and torn and twisted by atmospheric circulation on this planet. Quite the same as clouds in the atmosphere on the Earth are. Besides this, the axial turning of Jupiter brings an entirely different part of the planet into view every 2 or 3 hours, so that in making a map or chart of the planet, an arbitrary meridian must be selected. Even then, the process is not an easy one, and it is found that spots on Jupiter's equator turn round in 9 hours and 15 minutes, while other regions take a few minutes longer, the nearer the poles are approached. The Great Red Spot, about 30,000 miles long and a quarter as much in breadth, has been visible for about half a century. Bolton, an English observer, had made interesting studies of it very recently. The 4 moons, or satellites, which a small telescope reveals, are exceedingly interesting on many accounts. They were the first heavenly bodies seen by the aid of the telescope, Galileo having discovered them in 1610. They travel round Jupiter much the same as the moon does round the Earth, but faster. The innermost moon about 4 times per week, the second moon about twice a week, the third or largest moon, larger than the planet Mercury, once a week, and the outermost in about 16 days. The innermost is about 260,000 miles from Jupiter, and the outermost more than 1,000,000 miles. From their nearness to the huge and excessively hot globe of Jupiter, some astronomers, Proctor especially, have inclined to view that these little bodies may be inhabited. Jupiter has other moons, a very small one, close to the planet, which goes round in less than 12 hours, discovered by Barnard in 1892. 4 others are known, very small and faint and remote from the planet, which travel slowly round it in orbits of great magnitude. The 9th, or outermost, is at a distance of 15.5 million miles from Jupiter, and requires nearly 3 years in going round the planet. It was discovered by Nicholson at the Lick Observatory in 1914. The 8th was discovered by Malott at Greenwich in 1908, and is peculiar in the great angle of 28 degrees, at which its orbit is inclined to the equator of Jupiter. The 6th and 7th satellites revolve round Jupiter inside the 8th satellite, but outside the orbit of 4, and they were discovered by photography at the Lick Observatory in 1905 by Perrine, now director of the Argentine National Observatory at Cordoba. The ever-changing positions of the Medicean moons, as Galileo called the 4 satellites that he discovered, their passing into the shadow in eclipse, their transit in front of the disk, and their occultation behind it, form a succession of phenomena which the telescopist always views with delight. The times when all these events take place are predicted in the Nautical Almanac, many thousand of them each year, and the predictions cover 2 or 3 years in advance. Jupiter, as the naked eye sees him high up in the midnight sky, is the brightest of all the planets except Venus. Indeed, he is 5 times brighter than Sirius, the brightest of all the fixed stars. His stately motion among the stars will usually be visible by close observation from day to day, and his distance from the Earth at times when he is best seen is usually about 400 million miles. Jupiter travels all the way around the Sun in 12 years. His motion in orbit is about 8 miles a second. The eclipses of Jupiter's moons, caused by passing into the shadow of the planet, would take place at almost perfectly regular intervals if our distance from Jupiter were invariable. But it was early found out that while the Earth is approaching Jupiter, the eclipses take place earlier and earlier, but later and later when the Earth is moving away. The acceleration of the earliest eclipse added to the retardation of the latest makes 1,000 seconds, which is the time that light takes in crossing the diameter of the Earth's orbit around the Sun. Now, the velocity of light is well known to be 186,300 miles per second, so we calculate at once, and very simply, that the Sun's distance from the Earth, which is half the diameter of the orbit, equals 500 times 186,300,000, or 93 million miles. End of section 36.
Chapter 37 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Astronomy, the Science of the Heavenly Bodies, by David Todd. The Ringed Planet. Saturn is the most remote of all the planets that the ancient peoples knew anything about. These anciently known planets are sometimes called the lucid or naked eye planets, 5 in number: Mercury, Venus, Mars, Jupiter, and Saturn. Saturn shines as a first magnitude star with a steady straw-colored light, and is at a distance of about 800 million miles from the Earth when best seen. Saturn travels completely round the Sun in a little short of 30 years, and the telescope, when turned to Saturn, reveals a unique and astonishing object. A vast globe somewhat similar to Jupiter, but surrounded by a system of rings wholly unlike anything else in the universe, as far as at present known. The whole encircled by a family of 10 moons or satellites. The Saturnian system, therefore, is regarded by many as the most wonderful and most interesting of all the objects that the telescope reveals. At first, the flattening of the disk of Saturn is not easily made out, but every 15 years, as 1921 and 1936, the Earth comes into a position where we look directly at the thin edge of the rings, causing them to completely disappear. Then the remarkable flattening of the poles of Saturn is strikingly visible, amounting to as much as 1/10 of the entire diameter. The atmospheric belt system is also best seen at these times. But the rings of Saturn are easily the most fascinating features of the system. They can never be seen as if we were directly above or beneath the planet, so they never appear circular, as they really are in space, but always oval or elliptical in shape. The minor axis, or greatest breadth, is about 1/2 the major axis, or length. The latter is the outer ring's actual diameter, and it amounts to 170,000 miles, or 2 1/2 times the diameter of Saturn's globe. There are in fact no less than 4 rings. An outer ring, sometimes seen to be divided near its middle, an inner, broader, and brighter ring, and an innermost dusky or crepe ring, as it is often called. This comes within about 10,000 miles of the planet itself. After the form and size of the rings were well made out, their thickness, or rather lack of thickness, was a great puzzle. If a model about a foot in diameter were cut out of tissue paper, the relative proportion of size and thickness would be about right. In space, the thickness is very nearly 100 miles, so that, when we look at the ring system edge-on, it becomes all but invisible except in very large telescopes. Clearly, a ring so thin cannot be a continuous solid object, and recent observations have proved beyond a doubt that Saturn's rings are made up of millions of separate particles moving round the planet, each as if it were an individual satellite. Ever since 1857, the true theory of the constitution of the Saturnian ring has been recognized on theoretic grounds, because Clerk Maxwell founded the dynamical demonstration that the rings could be neither fluid nor solid, so that they must be made up of a vast multitude of particles traveling round the planet independently. But the physical demonstration that absolutely verified this conclusion did not come until 1895, when, as we have said in the preceding chapter, Keeler, by radial velocity measures on different regions of the ring by means of the spectroscope, proved that the inner parts of the ring travel more swiftly round the planet than the outer regions do. And he further showed that the rates of revolution in different parts of the ring exactly correspond to the periods of revolution which satellites of Saturn would have if at the same distance from the center of the planet. The innermost particles of the dusky ring, for example, travel round Saturn in about 5 hours, while the outermost particles of the outer bright ring take 137 hours to make their revolution. For many years, it was thought that the Saturnian ring system was a new satellite in process of formation, but this view is no longer entertained, and the system is regarded as a permanent feature of the planet, although astronomers are not in entire agreement as to the evolutionary process by which it came into existence, whether by some cosmic cataclysm or by gradual development throughout indefinite eons, as the rest of the solar system is thought to have come to its present state of existence. Possibly the planetesimal hypothesis of Chamberlain and Moulton affords the true explanation, as the result of a rupture due to excessive tidal strain. End of chapter 37, read by Andrea Kotzer.
Chapter 38 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Cosmic T. Astronomy, the Science of the Heavenly Bodies by David Todd. The Farthest Planets. On the 13th of March 1781, between 10 and 11 p.m., as Sir William Herschel was sweeping the constellation Gemini with one of his great reflecting telescopes, one star among all that passed through the field of view attracted his attention. Removing the eyepiece and applying another with a higher magnifying power, he found that, unlike all the other stars, this one had a small disk and was not a mere point of light, as all the fixed stars seemed to be. A few nights' observation showed that the stranger was moving among the stars, so he thought it must be a comet. But a week's observation following showed that he had discovered a new member of the planetary system far out beyond Saturn, which from time immemorial had been assumed to be the outermost planet of all. This then was the first real discovery of a planet, as the finding of the satellites of Jupiter had been the first of all astronomical discoveries. Herschel's discovery occasioned great excitement, and he named the new planet Georgium Sidus, or the Georgian, after his king. The king created him a knight and gave him a pension, besides providing the means for building a huge telescope 40 feet long, with which he subsequently made many other astronomical discoveries. The planet that Herschel discovered is now called Uranus. Uranus is an object not wholly impossible to see with the naked eye if the sky background is clear and black and one knows exactly where to look for it. Its brightness is about that of a sixth magnitude star or a little fainter. Its average distance from the Sun is about 1,800 million miles, and it takes 84 years to complete its journey round the Sun, traveling only a little more than 4 miles a second. When we examine Uranus closely with a large telescope, we find a small disk slightly greenish in tint, very slightly flattened, and at times faint bands or belts are apparently seen. Uranus is about 30,000 miles in diameter and is probably surrounded by a dense atmosphere. Its rotation time is 10 hours and 50 minutes. Uranus is attended by four moons or satellites named Ariel, Umbriel, Titania, and Oberon, the last being the most remote from the planet. This system of satellite has a remarkable peculiarity. The plane of the orbit in which they travel round Uranus is inclined about 80 degrees to the plane of the ecliptic, so that the satellite travel backward or in a retrograde direction, or we might regard their motion as forward or direct if we consider the planes of the orbit inclined at 100 degrees. For many years after the discovery of Uranus, it was thought that all the great bodies of solar system had surely been found. Least of all was any planet suspected beyond Uranus until the mathematical tables of the motion of Uranus, although built up and revised with the greatest care and thoroughness, began to show that some outside influence was disturbing it in accordance with Newton's law of gravitation. The attraction of a still more distant planet would account for the disturbance, and since no such planet was visible anywhere, a mathematical search for it was begun. Neptune. Wholly independently of each other, two young astronomers, Adams of England and Leverrier of France, undertook to solve the unique problem of finding out the position in the sky where a planet might be found that would exactly account for the irregular motion of Uranus. Both reached practically identical results. Adams was first in point of time, and his announcement led to the earliest observation without recognition of the new planet, July 30, 1846, although it was Leverrier's work that led directly to the new planet's being first seen and recognized as such September 23, 1846. Figuring backward, it was found that the planet had been accidentally observed in Paris in 1795, but its planetary character had been overlooked. Neptune is the name finally assigned to this historical planet. It is 30 times farther from the Sun than the Earth, or 2,800 million miles. Its velocity in orbit is a little over 3 miles per second, and it consumes 164 years in going once completely round the Sun. So faint is it that a telescope of large size is necessary to show it plainly. The brightness equals that of a star of the eighth magnitude, and with a telescope of sufficient magnifying power, the tiny disk can be seen and measured. The planet is about 30,000 miles in diameter and is not known to possess more than one moon or satellite. If there are others, they are probably too faint to be seen by any telescope at present in existence. End of chapter 38. Chapter 39 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Cosmic T. Astronomy, The Science of the Heavenly Bodies by David Todd. The Trans-Neptunian Planet. Investigation of the question of a possible trans-Neptunian planet was undertaken by the writer in 1877. As Neptune requires 164 years to travel completely round the Sun, and the period during which it has been carefully observed embraces only half that interval, clearly its orbit cannot be regarded as very well known. Any possible deviations from the mathematical orbit could not therefore be traced to the action of a possible unknown planet outside. But the case was different with Uranus, which showed very slight disturbances, and these were assumed to be due to a possible planet exterior to both Uranus and Neptune. As a position for this body in the heavens was indicated by the writer's investigation, that region of the sky was searched by him with great care in 1877-1878 with the 26-inch telescope at Washington, and photographs of the same region were afterward taken by others, though only with negative results. In 1880, Forbes of Edinburgh published his investigation of the problem from an entirely independent angle. Families of comets have long been recognized whose aphelion distances correspond so nearly with the distances of the planets that these comet families are now recognized as having been created by the several planets, which have reduced the high original velocities possessed by the comets on first entering the solar system. Their orbits have ever since been ellipses with their aphelia in groups corresponding to the distances of the planets concerned. Jupiter has a large group of such comets. Also Saturn. Uranus and Neptune likewise have their families of comets. And Forbes found two groups with average distances far outside of Neptune, from which he drew the inference that there are two trans-Neptunian planets. The position he assigned to the inner one agreed fairly well with the writer's planet as indicated by unexplained deviations of Uranus. The theoretical problem of trans-Neptunian planet has since been taken up by Galliot and Lau of Paris, the late Percival Lowell and W. H. Pickering of Harvard. The photographic method of search will, it is expected, ultimately lead to its discovery. On account of the probable faintness of the planet, at least the 12th or 13th magnitude, Metcalfe's method of search is well adapted to this practical problem. When near its opposition, the motion of Neptune retrograding among the stars amounts to 5 seconds of arc in an hour, while the trans-Neptunian planet would move by 3 seconds. By shifting the plate this amount hourly during exposure, the suspected object would readily be detected on the photographic plate as a minute and nearly circular disk, all the adjacent stars being represented by short trails. Interest in a possible planet or planets outside the orbit of Neptune is likely to increase rather than diminish. To the ancients, 7 was the perfect number. There were 7 heavenly bodies already known, so there could be no use whatever in looking for an eighth. The discovery of Uranus in 1781 proved the futility of such logic, and Neptune followed in 1846 with further demonstration if need be. The cosmogony of the present day sets no outer limits to the solar system, and some astronomers advocate the existence of many trans-Neptunian planets. End of chapter 39.
Chapter 40 of Astronomy, The Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Swan and Love. Astronomy, The Science of the Heavenly Bodies by David Todd. Comets, the hairy stars. Comets, hairy stars, as the origin of the name would indicate, are the freaks of the heavens, of great variety in shape, some with heads and some without, some with tails and some without, moving very slowly at one time and with exceedingly high velocity at another, in orbits at all possible angles of inclination to the general plane of the planetary paths round the sun. Their antics and irregularities were the wonder and terror of the ancient world, and they are keenly dreaded by superstitious people even to the present day. Down through the Middle Ages, the advent of a comet was regarded as threatening the world with famine, plague, and war, to princes, death, to kingdoms, many curses, to all estates, inevitable losses, to herdsmen rot, to ploughmen, hapless seasons, to sailors, storms, to cities, civil treasons. Comets appear to be marvelous objects, as well as sinister, chiefly because they bid apparent defiance to all law. Kepler had shown that the moon and the planets travel in regular paths, slightly elliptical to be sure, but nevertheless unvarying. None of the comets were known to follow regular paths till the time of Halley, late in the 17th century, when, as we have before told, a fine comet made its appearance, and Halley calculated its orbit with much precision, comparing this with the orbits of comets that had previously been seen. He found its path about the sun practically identical with that of at least two comets previously observed in 1531 and 1607. So Halley ventured to think that all these comets were one and the same body, and that it traveled round the sun in a long ellipse in a period of about 75 or 76 years. We have seen how his prediction of its return in 1758 was verified in every particular. On the comet's return in 1910, Crowell and Cromelin of Greenwich made a thorough mathematical investigation of the orbit, indicating that the year 1986 will witness its next return to the sun. There is a class of astronomers known as comet hunters, and they pass hours upon hours of clear, sparkling, moonless nights in search for comets. They are equipped with a peculiar sort of telescope called a comet seeker, which has an object glass usually 4 or 5 inches in diameter, and a relatively short length of focus, so that a larger field of view may be included. Regions near the poles of the heavens are perhaps the most fruitful fields for search, and thence toward the sun, till its light renders the sky too bright for the finding of such a faint object as a new comet usually is at the time of discovery. Generally, when first seen, it resembles a small circular patch of faint luminous cloud. When a suspect is found, the first thing to do is to observe its position accurately with relation to the surrounding stars. Then, if on the next occasion when it is seen the object has moved, the chances are that it is a comet, and a few days' observation will provide material from which the path of the comet in space can be calculated. By comparing this with the complete lists of comets, now about 700 in number, it is possible to tell whether the comet is a new one or an old one returning. The total number of comets in the heavens must be very great, and thousands are doubtless passing continually undetected, because their light is wholly overpowered by that of the sun. Of those that are known, perhaps 1 in 12 develops into a naked-eye comet, and in some years 6 or 7 will be discovered. With sufficiently powerful telescopes, there are, as a rule, not many weeks in the year when no comet is visible. Brilliant naked-eye comets are, however, infrequent. Comets, except Halley's, generally bear the name of their discoverer, as Donati, 1858, and Pons Brooks in 1893. Pons was a very active discoverer of comets in France early in the 19th century. He was a doorkeeper at the Observatory of Marseille, and his name is now more famous in astronomy than that of Thales, then the director of the observatory, who taught and encouraged him. Messier was another very successful discoverer of comets in France, and in America we have had many. Swift, Brooks, and Barnard, the most successful. How bright a comet will be and how long it will be visible depends on many conditions, so the comets vary much in these respects. The first comet of 1811 was under observation for nearly a year and a half, the longest on record till Halley's in 1910. In case a comet eludes discovery and observation until it has passed its perihelion, or nearest point to the Sun, its period of visibility may be reduced to a few weeks only. The brightest comets on record were visible in 1843 and 1882. So brilliant were they that even the effulgence of full daylight did not overpower them. In particular, the comet of 1843 was not only excessively bright, but at its nearest approach to the Earth, its tail swept all the way across the sky, from one horizon to the other. It must have looked very much like the straight beam of an enormous searchlight, though very much brighter. The tails of comets are to the naked eye the most compelling thing about them, and to the ancient peoples they were naturally most terrifying. Their tails are not only curved, but sometimes curved with varying degrees of curvature, and this circumstance adds to their weirdness of appearance. If we examine the tail of a comet with a telescope, it vanishes as if there were nothing to it, as indeed one may almost say there is not. Ordinarily, only the head of the comet is of much interest in the telescope. When first seen, there is usually nothing but the head visible, and that is made up of portions which develop more or less rapidly, presenting a succession of phenomena quite different in different comets. When first discovered, a comet is usually at a great distance from the Sun, about the distance of Jupiter, and we see it not as we do the planets, by sunlight reflected from them, but by the comet's own light. This is, at the time, very faint, and nearly all comets at such distance look alike. Small, roundish, hazy patches of faint cloud-like light, with very often a concentration towards the center called the nucleus, on the average about 4,000 miles in diameter. Approach towards the Sun brightens up the comet more and more, and the nucleus usually becomes very much brighter and more star-like. Then, on the sunward side of the nucleus, jet-like streamers or envelopes appear to be thrown off, often as if in parallel curved strata, or concentrically. As they expand and move outward from the nucleus, these envelopes grow fainter and are finally merged in the general nebulosity known as the comet's head, which is anywhere from 30,000 to 100,000 miles in diameter. As a rule, this is an orderly development which can be watched in the telescope from hour to hour and from night to night. But occasionally, a cometary visitor is quite a law to itself in development, presenting a fascinating succession of unpredictable surprises. Then follows the development of the comet's tail, perhaps more striking than anything that has preceded it. Here, a genuine repulsion from the Sun appears to come into play. It may be an electrical repulsion. Much of the material projected from the comet's nucleus seems to be driven backward or repelled by the Sun, and it is this that goes to form the tail. The particles which form the tail then travel in modified paths, which nevertheless can be calculated. The tail is made up of these luminous particles and expands in space, much in the form of a hollow, horn-shaped cone, the nucleus being near the tip of the horn. Some comets possess multiple tails with different degrees of curvature. Donati's, for example. Usually, there is a nearly straight central dark space marking the axis of the comet and following the nucleus, but occasionally this is replaced by a thin light streak very much less in breadth than the diameter of the head. Cometary tails are sometimes 100 million miles in length. 3 different types of cometary tails are recognized. First, the long straight ones, apparently made up of matter repelled by the sun 12 to 15 times more powerfully than gravitation attracts it. Such particles must be brushed away from the comet's head with a velocity of perhaps 5 miles a second, and their speed is continually increasing. Probably these straight tails are due to hydrogen. The second type tails are somewhat curved or plume-like, and they form the most common type of cometary tail. In them, the sun's repulsion is perhaps twice its gravitational attraction, and hydrocarbons in some form appear to be responsible for tails of this character. Then there is a third type, much less often seen, short and quickly curving, probably due to heavier vapors, as of chlorine or iron, or sodium, in which the repulsive force is only a small fraction of that of gravitation. Many features of this theory of cometary tails are born out of investigation of their light with the spectroscope, although the investigation is as yet fragmentary. It is evident that the tail of a comet is formed at the expense of the substance of the nucleus and head, so that the matter repelled is forever dissipated through the regions of space which the comet has traveled. Comets must lose much of their original substance every time they return to perihelion. Comets actually age, therefore, and grow less and less in magnitude of material, as well as brightness, until they are at last opaque, non-luminous bodies, which it becomes impossible to follow with the telescope. End of chapter 40.
Chapter 41 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Cosmic T. Astronomy, the Science of the Heavenly Bodies by David Todd. Where do comets come from? Where do comets come from? The answer to this question is not yet fully made out. Most likely, they have not all had a similar origin, and theories are abundant. Apparently, they come into the solar system from outer space from any direction whatsoever. The depths of the interstellar space seem to be responsible for most, if not all, of the new ones. Whether they have come from other stars or stellar systems, we cannot say. While comets are tremendous in size or volume, their mass or the amount of real substance in them is relatively very slight. We know this by the effect they produce on planets that they pass near, or rather by the effect that they fail to produce. The Earth's atmosphere weighs about 1/250,000th as much as the Earth itself, but a comet's entire mass must be vastly less than this. Even if a comet were to collide with the Earth head-on, there is little reason to believe that dire catastrophe would ensue. At least twice the Earth is known to have passed through the tail of a comet, and the only effect noticed was upon the comet itself. Its orbit had been moved somewhat by the attraction of the Earth. If the comet were a small one, collision with any of the planets would result in absorption and dissipation of the comet into vapor. The whole of a large comet has perhaps as much mass or weight as a spear of iron 100 miles in diameter. Even this could not wreck the Earth, but the effect would depend upon what part of the Earth was hit. A comet is very thin and tenuous because its relatively small mass is distributed through a volume so enormous. So it is probable that the Earth's atmosphere could scatter and burn up the invading comet, and we should have only a shower of meteors on an unprecedented scale. Diffusion of noxious gases through the atmosphere might vitiate it to some extent, though probably not enough to cause the extinction of animal life. Every comet has an interesting history of its own, almost indeed unique. One of the smallest comets and the briefest in its period round the Sun is known as Encke's comet. It is a telescopic comet with a very short tail. Its time of revolution is about 3.5 years, and it exhibits a remarkable contraction of volume on approach to the Sun. Biela's comet has a period about twice as long. At one time, it passes within about 15 million miles of the Earth, and somewhere about the year 1840, this comet divided into two distinct comets, which traveled for months side by side, but later separated, and both have since completely disappeared. Perhaps the most beautiful of all comets is that discovered by Donati of Florence in 1858. Its coma presented the development of jets and envelopes in remarkable perfection, and its tail was of the secondary or hydrocarbon type, but accompanied by two faint streamer tails nearly tangential to the main tail and of the hydrogen type. Donati's comet moves in an ellipse of extraordinary length, and it will not return to the Sun for nearly 2,000 years. The most brilliant comet of the last half-century is known as the Great Comet of 1882. In a clear sky, it could readily be seen at midday. On September 17, it passed across the disk of the Sun and was practically as bright as the surface of the Sun itself. The comet had a multiple nucleus and a hydrocarbon tail of the second type, nearly 100 million miles in length. Doubtless, this great comet is a member of what is known as a cometary group, which consists of comets having the same orbit and traveling tandem round the Sun. The comet of 1668, 1843, 1880, 1882, and 1887 belong to this particular group, and they all pass within 300,000 miles of the Sun's surface at a maximum velocity exceeding 300 miles a second. They must therefore invade the region of the solar corona, the inference being that the corona, as well as the comet, is composed of exceedingly rare matter. Photography of comets has developed remarkably within recent years, especially under the deft manipulation of Barnard, whose plates, in particular during his residence at the Lick Observatory on Mount Hamilton, California, show the feature of cometary heads and tails in excellent definition. Halley's comet at the 1910 apparition was particularly well photographed at many observatories. The question is often asked, when will the next comet come? If a large bright comet is meant, astronomers cannot tell. At almost any time one may blaze into prominence within only a few days. During the latter half of the last century, bright comets appeared at perihelion at intervals of 8 years on the average. Several of the lesser and fainter periodic comets return nearly every year, but they are mostly telescopic and are rarely seen except by astronomers who are particularly interested in observing them. End of chapter 41.
Chapter 42 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Astronomy, the Science of the Heavenly Bodies, by David Todd. Meteors and Shooting Stars. Falling stars or shooting stars have been familiar sights in all ages of the world, but the ancient philosophers thought them scarcely worthy of notice. According to Aristotle, they were mere nothings of the upper atmosphere, of no more account than the general happenings of the weather. But about the end of the 18th century and the beginning of the 19th, the insufficiency of this view began to be fully recognized, and interplanetary space was conceived as tenanted by shoals of moving bodies exceedingly small in mass and dimension as compared with the planets. Millions of these bodies are all the time in collision with the outlying regions of our atmosphere, and by their impact upon it and their friction in passing swiftly through it, they become heated to incandescence, thus creating the luminous appearances commonly known as shooting stars. For the most part, they are consumed or dissipated in vapor before reaching the solid surface of the earth, but occasionally a luminous cloud or streak is left glowing in the wake of a large meteor, which sometimes remains visible for half an hour after the passage of the meteor itself. These mist-like clouds projected upon the dark sky have been especially studied by Trowbridge of Columbia University. Many more meteors are seen during the morning hours, say from 4 to 6, than at any other nightly period of equal length, because the visible sky is at that time nearly centered around the general direction toward which the Earth is moving in its orbit round the Sun, so that the number of meteors that would fall upon the Earth if at rest is increased by those which the Earth overtakes by its own motion. Also, from January to July, while the Earth is traveling from perihelion to aphelion, fewer meteors are seen than in the last half of the year, but this is chiefly because of the rich showers encountered in August and November. Although the descent of meteoric bodies from the sky was pretty generally discredited until early in the 19th century, such falls had nevertheless been recorded from very early times. They were usually regarded as prodigies or miracles, and such stones were commonly objects of worship among ancient peoples. For example, the Phrygian stone, known as the, quote, Diana of the Ephesians, which fell down from Jupiter, unquote, was a famous stone built into the Kaaba at Mecca, and even today it is revered by Mohammedans as a holy relic. Perhaps the earliest known meteoric fall is that historically recorded in the Parian Chronicle as having occurred in the island of Crete, BC 1478. Also in the Imperial Museum of Petrograd is the Pallas or Krasnoyarsk iron, perhaps 3/4 of a ton in weight, found in 1772 by Pallas, the famous traveler, at Krasnoyarsk, Siberia. But a fall of meteoric stones that chanced upon the department of Orne, France, in 1805, led to a critical investigation by Biot, the distinguished physicist and academician. According to his report, a violent explosion in the neighborhood of L'Aigle had been heard for a distance of 75 miles around and lasting 5 or 6 minutes about 1 p.m. on Tuesday, April 26. From several adjoining towns, a rapidly moving fireball had been seen in a sky generally clear, and there was absolutely no room for doubt that on the same day many stones fell in the neighborhood of L'Aigle. Biot estimated their number between 2,000 and 3,000, and they were scattered over an elliptical area more than 6 miles long and 2.5 miles broad. Thenceforward, the descent of meteoric matter from outer space upon the Earth has been recognized as an unquestioned fact. The origin of these bodies being cosmic, meteors may be expected to fall upon the Earth without reference to latitude or season or day and night or weather. On entering our upper atmosphere, their temperature must be that of space, many hundred degrees below zero, and their velocities range from 10 miles per second upward. But atmospheric resistance to their flight is so great that their velocity is quickly reduced. At ground impact, it does not exceed a few hundred feet per second. On January 1, 1869, several meteoric stones fell on ice only a few inches thick in Sweden, rebounding without either breaking through the ice or being themselves fractured. Naturally, the flight of a meteor through the atmosphere will be only a few seconds in duration, and owing to the sudden reduction of velocity, it will continue to be luminous throughout only the upper part of its course. Visibility generally begins at an elevation of about 70 miles and ends at perhaps half that altitude. What is the origin of meteors? Theories there are in great abundance: that they come from the sun, that they come from the moon, that they come from the earth in past ages as a result of volcanic action, and so on. But there are many difficulties in the way of acceptance of these and several other theories. That all meteors were originally parts of cometary masses is, however, a theory that may be accepted without much hesitation. Comets have been known to disintegrate. Biela's comet even disappeared entirely, so that during a shower of Biela meteors in November 1885, an actual fragment of the lost comet fell upon the Earth at Mazapil, Mexico. As the Belid meteors encounter the Earth with a relatively low velocity of 10 miles a second, we may expect to capture other fragments in the future. Numerous observers saw the weird disintegration of the nucleus of the Great Comet of 1882, well recognized as a member of the family of the Comet of 1843. As these comets are fellow voyagers through space along the same orbit, probably all 5 members of the family, with perhaps others, were originally a single comet of unparalleled magnitude. The Brooks Comet of 1890 affords another instance of fragmentary nucleus. The oft-repeated action of solar forces tending to disrupt the mass of a comet more and more, and scatter its material throughout space, the secular dismemberment of all comets becomes an obvious conclusion. During the hundreds of millions of years that these forces are known to have been operant, the original comets have been broken up in great numbers, so that elliptical rings of opaque meteoric bodies now travel round the Sun in place of the comets. These bodies in vast numbers are everywhere through space, each too small to reflect an appreciable amount of sunlight and becoming visible only when they come into collision with our outer atmosphere. The practical identity of several such meteor streams and cometary orbits has already been established, and there is every reason for assigning a similar origin to all meteoric bodies. Meteors, then, were originally parts of comets, which have trailed themselves out to such extent that particles of the primal masses are liable to be picked up anywhere along the original cometary paths. The historical records of all countries contain trustworthy accounts of meteoric showers. Making due allowances for the flowery imagery of the Oriental, it is evident that all have at one time or another seen much the same thing. In A.D. 472, for instance, the Constantinople sky was reported alive with flying stars. In October 1202, quote, "Stars appeared like waves upon the sky, and they flew about like grasshoppers." Unquote. During the reign of King William II occurred a very remarkable shower in which, quote, "stars seemed to fall like rain from heaven." Unquote. But the showers of November 1799 and 1833 are easily the most striking of all. The sky was filled with innumerable fiery trails, and there was not a space in the heavens, a few times the size of the moon, that was not ablaze with celestial fireworks. Frequently, huge meteors blended their dazzling brilliancy with the long and seemingly phosphorescent trails of the shooting stars. The interval of 34 years between 1799 and 1833 appeared to indicate the possibility of a return of the shower in November of 1866 or 1867. And all the people of that day were aroused on this subject and made every preparation to witness the spectacle. Extemporized observatories were established, watchmen were everywhere on the lookout, and bells were to be rung the minute the shower began. The newspapers of the day did little to allay the fears of the multitude, but the critical days of November 1866 passed with disappointment in America. In Europe, however, a fine shower was seen, though it was not equal to that of 1833. The astronomers at Greenwich counted many thousand meteors. In November of 1867, however, American astronomers were gratified by a grand display, which, although failing to match the general expectation, nevertheless was a most striking spectacle, and the careful preparation for observing it afforded data of observation which were of the greatest scientific value. The actual orbits of these bodies in space became known with great exactitude, and it was found that their general path was identical with that of the first comet of 1866, which travels outward somewhat beyond the planet Uranus. When the visible paths of these meteors are traced backward, all appear as if they originated from the constellation Leo. So they are known as the Leonids, and a return of the shower was confidently predicted for November 1900 and 1901, which for unknown reasons failed to appear. During the last half-century, meteors have been pretty systematically observed, especially by the astronomers of Italy and Denning of England, so that several hundred distinct showers are now known. Their radiant points fall in every part of the heavens, and there is scarcely a clear moonless night when careful watching for meteors will be unrewarded. Besides November, the months of August, Perseids, April, Lyrids, and December, Geminids, are favorable. Following in tabular form is a fairly comprehensive list of the meteoric showers of the year and the epochs of the showers according to Denning. Name of shower, date of shower. Quadrantids, January 2nd through the 4th. Zeta Cepheids, January 25th. Alpha Leonids, February 19th through March 1st. Tau Leonids, March 1st through the 4th. Beta Ursids, March 13th through the 24th. Lyrids, April 20th to the 22nd. Gamma Aquarids, May 1st through the 6th. Zeta Herculids, May 18th through the 26th. Eta Pegasids, May 30th to June 4th. Theta Boötids, June 27th through the 28th. Alpha Capricornids, July 15th through the 28th. Delta Aquarids, July 25th through the 30th. Perseids, August 10th through the 12th. Omicron Draconids, August 15th through the 25th. Zeta Draconids, August 21st through September 2nd. Piscids, September 4th through the 14th. Alpha Andromedids, September 27th. Epsilon Aretids, October 11th through the 24th. Orionids, October 17th through the 24th. Epsilon Perseids, November 5th. Leonids, November 13th through the 15th. Epsilon Taurids, November 14th through the 25th. Andromedids, November 17th through the 23rd. Beta Geminids, December 1st through the 12th. Geminids, December 1st through the 14th. Alpha Ursae Majorids, December 18th through the 21st. Kappa Draconids, December 18th through the 28th. The year 1916 was exceptional in providing an abundant and previously unknown shower on June 28, and its stream has nearly the same orbit as that of the Pons Veneca periodic comet. Useful observations of meteors are not difficult to make, and they are of service to professional astronomers investigating the orbits of these bodies, among whom are Mitchell and Olivier of the University of Virginia. End of Chapter 42. Chapter 43 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Astronomy, the Science of the Heavenly Bodies by David Todd. Meteorites. Meteorites, the name for meteors which have actually gone all the way through our atmosphere, are never regular in form or spherical. As a rule, the iron meteorites are covered with pittings or thumb marks, due probably to the resistance and impact of the little columns of air which impede its progress, together with the unequal condition and fusibility of their surface material. The work done by the atmosphere in suddenly checking the meteor's velocity appears in considerable part as heat, fusing the exterior to incandescence. This thin liquid shell is quickly brushed off, making oftentimes a luminous train. But notwithstanding the exceedingly high temperature of the exterior enforced upon it for the brief time of transit through the atmosphere, it is probable that all large meteorites, if they could be reached at once on striking the earth, would be found to be cold, because the smooth black, varnish-like crust, which always encases them as a result of intense heat, is never thick. On one occasion, a meteor which was seen to fall in India was dug out of the ground as quickly as possible, and found to be not hot as was expected, but coated thickly over with ice frozen on it from the moisture in the surrounding soil. As to the composition of shooting stars and their probable mass and its effect upon the earth, our data are quite insufficient. The lines of sodium and magnesium have been hurriedly caught in the spectroscope, and estimating on the basis of the light emitted by them, the largest meteors must weigh ounces rather than pounds. Nevertheless, it is interesting to inquire what addition the continual fall of many millions daily upon the earth makes to its weight. Somewhere between 30 and 50,000 tons annually is perhaps a conservative estimate, but even this would not accumulate a layer 1 inch in thickness over the entire surface of the earth in less than 1,000 million years. Many hundreds of the meteors actually seen to fall, together with those picked up accidentally, are recovered and prized as specimens of great value in our collections, the richest of which are now in New York, Paris, and London. The detailed investigation of them are rather the province of the chemist, the crystallographer, and the mineralogist than of the astronomer, whose interest is more keen in their life history before they reach the Earth. To distinguish a stony meteorite from terrestrial rock substances is not always easy, but there is usually little difficulty in pronouncing upon an iron meteorite. These are most frequently found in deserts because the dryness of the climate renders their oxidation and gradual disappearance very slow. The surface of a suspected iron meteorite is polished to a high luster, and nitric acid is poured upon it. If it quickly becomes etched with a characteristic series of lines, or a sort of cross-hatching, it is almost certain to be a meteorite. Occasionally carbon has been found in meteorites, and the existence of diamond has been suspected. The minerals composing meteorites are not unlike terrestrial materials of volcanic origin, though many of them are peculiar to meteorites only. More than 1/3 of all the known chemical elements have been found by analysis in meteorites, but not any new ones. Meteoric iron is a rich alloy containing about 10% of nickel, also cobalt, tin, and copper, in much smaller amount. Calcium, chlorine, sodium, and sulfur likewise are found in meteoric irons. At very high temperatures, iron will absorb gases and retain them until again heated to red heat. Carbonic oxide, helium, hydrogen, and nitrogen are thus imprisoned or occluded in meteoric irons in very small quantities. And in 1867, during a London lecture by Graham, a room in the Royal Institution was for a brief space illuminated by gas brought to Earth in a meteorite from interplanetary space. Meteorites, too, have been most critically investigated by the biologist, but no trace of germs of organic life of any type has so far been found. Farrington of Chicago has published a full descriptive catalog of all the North American meteorites. Recent investigations of radioactivity of meteorites show that the average stone meteorite is much less radioactive than the average rock, and probably less than 1/4 as radioactive as in average granite. The metallic meteorites examined were found about wholly free from radioactivity. From shooting stars, perhaps the chips of the celestial workshop, or more possibly related to the planetesimals which the processes of the growth of the universe have swept up into the vastly greater bodies of the universe, transition is natural to the stars themselves, the most numerous of the heavenly bodies, all shining by their own light, and all conceivably remote from the solar system, which nevertheless appears to be not far removed from the center of the stellar universe. End of chapter 43. Chapter 44 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Astronomy, the Science of the Heavenly Bodies by David Todd. The Universe of Stars. Our consideration of the solar system hitherto has kept us quite at home in the universe. The outer known planets, Uranus and Neptune, are indeed far removed from the Sun, and a few of the comets that belong to our family travel to even greater distances before they begin to retrace their steps sunward. When we come to consider the vast majority of the glistening points on the celestial sphere, all in fact except the 5 great planets, Mercury, Venus, Mars, Jupiter, and Saturn, we are dealing with bodies that are self-luminous like the Sun, but that vary in size quite as the bodies of the solar system do, some stars being smaller than the Sun and others many hundredfold larger than he is, some being giants and others dwarfs. But the overwhelming remoteness of all these bodies arrests our attention, and even taxes our credulity regarding the methods that astronomers have depended on to ascertain their distances from us. Their seeming countlessness, too, is as bewildering as are the distances, though if we make actual counts of those visible to the naked eye within a certain area, in the body of the Great Bear, for example, the great surprise will be that there are so few, and if the entire dome of the sky is counted at any one time, a clear, moonless sky would reveal perhaps 2,500, so that in the entire sky, northern and southern, we might expect to find 5,000 to 6,000 lucid stars, or stars visible to the naked eye. But when the telescope is applied, every accession of power increases the myriads of fainter and fainter stars, until the number within optical reach of present instruments is somewhere between 400 and 500 millions. But if we were to push the 100-inch reflector on Mount Wilson to its limit by photography, with plates of the highest sensitiveness, millions upon millions of excessively faint stars would be plainly visible on the plates, which the human eye can never hope to see directly with any telescope present or future, and which would doubtless swell the total number of stars to 1,000 millions. Recent counts of stars by Chapman and Melotte of Greenwich tend to substantiate this estimate. What have astronomers done to classify or catalog this vast array of bodies in the sky? Even before making any attempt to estimate their number, there is a system of classification simply by the amount of light they send us or by their apparent stellar magnitudes. Not their actual magnitudes, for of those we know as yet very little. We speak of stars of the first magnitude, of which there are about 20, Sirius being the brightest and Regulus the faintest. Then there are about 65 of the second or next fainter magnitude, stars like Polaris, for example, which give an amount of light 2.5 times less than the average first magnitude star. Stars of the third magnitude are fainter than those of the second in the same ratio, but their number increases to 200, fourth magnitude 500, fifth magnitude 1400, sixth magnitude 5000, and these are so faint that they are just visible on the best nights without telescopic aid. Decimals express all intermediate graduations of magnitude. Astronomers carry the telescopic magnitudes much farther till a magnitude beyond the 20th is reached, preserving in every case the ratio of 2 1/2 for each magnitude in relation to that numerically next to it. Even Jupiter and Venus and the Sun and Moon are sometimes calculated on this scale of stellar magnitude, numerically negative, of course, Venus sometimes being as bright as magnitude -4.3 and the Sun -26.7. Knowing thus the relation of Sun, Moon, and stars, and the number of stars of different magnitudes, it is possible to estimate the total light from the stars. This interesting relation comes out this way, that the stars we cannot see with the naked eye give a greater total of light than those we can because of their vastly greater numbers. And if we calculate the total light of all the brighter stars down to magnitude 9 1/2, we find it equal to 1/80th of the light of the average full moon. Many stars show marked differences in color, and strictly speaking, the stars are now classified by their colors. The atmosphere affects star colors very considerably, low altitudes or greater thickness of air absorbing the bluish rays more strongly and making the stars appear redder than they really are. Aldebaran, Betelgeuse, and Antares are well-known red stars, Capella and Alpha Cetae yellowish, Vega and Sirius blue, and Procyon and Polaris white. Among the telescopic stars are many of a deep blood-red tint, variable stars being numerous among them. Double stars, too, are often complementary in color. There is evidence indicating change of color of a very few stars in long periods of time. Sirius, for example, 2,000 years ago, was a red star, now it is blue or bluish-white. But the meaning of color or change of color in a star is as yet only incompletely ascertained. It may be connected with the radiative intensity of the star, or its age, or both. The late Professor Edward C. Pickering was famous for his lifelong study and determination of the magnitudes of the stars. Standards of comparison have been many and have led to much unnecessary work. Pickering chose Polaris as a standard and devised the meridian photometer, an ingenious instrument of high accuracy in which the light of a star is compared directly with that of the pole star by reflection. All the bright stars of both the northern and the southern skies are worked into a standard system of magnitudes known as HP, or the Harvard photometry. Astronomers make use of several different kinds of magnitude for the stars. The apparent magnitude, as the eye sees it, often called the visual magnitude, the photographic magnitude, as the photographic plate records it, and these are now determined with the highest accuracy. The photovisual magnitude, quite the same as the visual, but determined photographically on an isochromatic plate with a yellow screen or filter, so that the intensity is nearly the same as it appears to the eye. The difference between the star's visual or photovisual magnitude and its photographic magnitude is called its color index, and is often used as a measure of the star's color. Light of shorter wavelengths, as blue and violet, affects the photographic plate more rapidly than the reds and yellows of longer wavelengths, by which the eye mainly sees, so that red stars will appear much fainter and blue stars much brighter on the ordinary photographic plate than the eye sees them. So great are the differences of color in the stars that well-known asterisms, with which the eye is perfectly familiar, are sometimes quite unrecognizable on the photographic plate, except by relative positions of the stars composing them. White stars affect the eye and the plate about equally, so that their visual or photovisual and photographic magnitudes are about equal. The studies of the colors of the stars, the different methods of determining them, and the relations of color to constitution have been made the subject of a special investigation by Sears of Mount Wilson and many other astronomers. Centuries of work of astronomers have been faithfully devoted to mapping or charting the stars and cataloging them. Just as we have geographical maps of countries, so the heavens are parceled out in sections and the stars set down in their true relative positions, just as cities are on the map. Recent years have added photographic charts, especially of detailed regions of the sky, but owing to spectral differences of the stars, their photographic magnitudes are often quite different from their visual magnitudes. From these maps and charts, the positions of the stars can be found with much precision. But if we want the utmost accuracy, we must go to the star catalogues, huge volumes, oftentimes, with stellar positions set down therein with the last degree of precision. First there will be the star's name, and in the next column its magnitude, and in the third the star's right ascension. This is its angular distance eastward around the celestial sphere starting from the vernal equinox, and it corresponds quite closely to the longitude of a place which we should get from a gazetteer if we wished to locate it on the earth. Then another column of the catalogue will give the star's declination, north or south of the equator, just as the gazetteer will locate a city by its north or south latitude. End of chapter 44.
Chapter 45 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in December 2021. Astronomy, the Science of the Heavenly Bodies, by David Todd. Chapter 45. Star Charts and Catalogues. Who made the first star chart or catalogue? There is little doubt that Eudoxus, BC 200, was the first to set down the positions of all the brighter stars on a celestial globe, and he did this from observations with a gnomon and an armillary sphere. Later, Hipparchus, BC 130, constructed the first known catalogue of stars, so that astronomers of a later day might discover what changes are in progress among the stars, either in their relative positions or caused by old stars disappearing or new stars appearing at times in the heavens. Hipparchus was an accurate observer, and he discovered an apparent and perpetual shifting of the vernal equinox westward, by which the right ascensions of the stars are all the time increasing. He determined the amount of it pretty accurately too. His catalogue contained 1080 stars, and is printed in the Almagest of Ptolemy. Centuries elapsed before a second star catalogue was made by Ulugh Beg, an Arabian astronomer, AD 1420, who was a son of Tamerlane, the Tartar monarch of Samarkand, where the observations for the catalogue were made. The stars were mainly those of Ptolemy, and much the same stars were re-observed by Tycho Brahe, AD 1580, with his greatly improved instruments, thus forming the third and last star catalogue of importance before the invention of the telescope. From the end of the 17th century onward, the application of the telescope to all the types of instruments for making observations of star places has increased the accuracy many-fold. The entire heavens has been covered by Argelander in the northern hemisphere and Gould in the southern, over 700,000 stars in all. Many government observatories are still at work cataloguing the stars. The Carnegie Institution of Washington maintains a department of astrometry under Boss of Albany, which has already issued a preliminary catalogue of more than 6,000 stars, and has a great general catalogue in progress, together with investigations of stellar motions and parallaxes. This catalogue of star positions will include proper motions of stars to the 7th magnitude. In 1887, on proposal of the late Sir David Gill, an international congress of astronomers met at Paris and arranged for the construction of a photographic chart of the entire heavens, allotting the work to 18 observatories, equipped with photographic telescopes essentially alike. The total number of plates exceeds 25,000. Stars of the 14th magnitude are recorded, but only those including the 11th magnitude will be catalogued, perhaps 2 million in all. The expense of this comprehensive map of the stars has already exceeded $2 million, and the work is now nearly complete. Turner of Oxford has conducted many special investigations that have greatly enhanced the progress of this international enterprise. Other great photographic star charts have been carried through by the Harvard Observatory with the annex at Arequipa, Peru, employing the Bruce photographic telescope, a doublet with 24-inch lenses. Also, Kaptein of Groningen has catalogued about 300,000 stars on plates taken at Cape Town. Charting and cataloguing the stars, both visually and photographically, is a work that will never be entirely finished. Improvements in processes will be such that it can be better done in the future than it is now, and the detection of changes in the fainter stars and investigation of their motions will necessitate repetition of the entire work from century to century. The origin of the names of individual stars is a question of much interest. The constellation figures form the basis of the method, and the earliest names were given according to location in the especial figure, as for instance Cor Scorpii, the heart of the scorpion, later known as Antares or Alpha Scorpii. The Arabians adopted many star names from the Greeks, and gave about 100 special names to other stars. Some of these are in common use today by navigators, observers of meteors, and of variable stars. Sirius, Vega, Arcturus, and a few other first magnitude stars are instances. But this method is quite insufficient for the fainter stars whose numbers increase so rapidly. Bayer, a contemporary of Galileo, originated our present system, which also employs the names of the constellations, the Latin genitive in each case, prefixed by the small letters of the Greek alphabet, from alpha to omega, in order of decreasing brightness, and followed by the Roman letters when the Greek alphabet is exhausted. If there were still stars left in a constellation unnamed, numbers were used, first by Flamsteed, Astronomer Royal, and numbers in the order of right ascension in various catalogues are used to designate hundreds of other stars. The vast bulk of the stars are, however, nameless, but about 1 million are identifiable by their positions, right ascension and declination, on the celestial sphere. End of chapter 45. Chapter 46 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai. in December 2021. Astronomy, The Science of the Heavenly Bodies, by David Todd. Chapter 46, The Sun's Motion Toward Lyra. If Hipparchus or Galileo should return to Earth tonight and look at the stars and constellations as we see them, there would be no change whatever discernible in either the brightness of the stars or in their relative positions. So the name fixed stars would appear to have been well chosen. Halley, in the 17th century, was the first to detect that slow relative change of position of a few stars, which is known as proper motion, and all the modern catalogues give the proper motions in both right ascension and declination. These are simply the small annual changes in position athwart the line of vision, and, as a whole, the proper motions of the brighter stars exceed the corresponding motions of the fainter ones because they are nearer to us. The average proper motion of the brightest stars is 0.25 seconds, and of stars of the sixth magnitude, only 1/6 as great. A few extreme cases of proper motion have been detected, one as large as 9 seconds, of an orange-yellow star of the 8th magnitude in the southern constellation Pictor, and Barnard has recently discovered a star with a proper motion exceeding 10 seconds. Several determinations of its parallax give 0.52 seconds, corresponding to a distance of 6.27 light-years. Nevertheless, 2 centuries would elapse before these stars would be displaced as much as the breadth of the moon among their neighbors in the sky. The proper motions of stars are along perfectly straight lines, so far as yet observed. Ultimately, we may find a few moving in curved paths or orbits, but this is hardly likely. As for a central sun hypothesis, that pointing out Alcyone in particular, there is no reliable evidence whatever. Analysis of the proper motions of stars in considerable numbers, first by Sir William Herschel, showed that they were moving radially from the constellation Hercules, and in great numbers also towards the opposite side of the stellar sphere. Later investigation places this point, called the sun's goal, or apex of the sun's way, over in the adjacent constellation Lyra, and the opposite point, or the sun's quit, is about halfway between Sirius and Canopus. By means of the radial velocities of stars in these antipodal regions of the sky, it is found that the sun's motion toward Lyra, carrying all his planetary family along with him, is taking place at the rate of about 12 miles in every second. While the right ascensions of the solar apex, as given by the different investigations, have been pretty uniform, the declination of this point has shown a rather wide variation not yet explained. For example, there is a difference of nearly 10 degrees between the declination, 34.3 degrees, of the apex, as determined by Bose, from the proper motions of more than 6,000 stars, and the declination, 25.3 degrees, found by Campbell from the radial velocities of nearly 1,200 stars. Several investigations tend to show that the fainter the stars are, the greater is the declination of the solar apex. More remarkable is the evidence that this declination varies with the spectral type of the stars, the later types, especially G and K, giving much more northerly values. On the whole, the great amount of research that has been devoted to the solar motion relative to the system of the stars for the past 100 years may be said to indicate a point in right ascension 18 hours, 270 degrees, and declination 34 degrees north, as the direction toward which the sun is moving. This is not very far from the bright star Alpha Lyrae, and the antipodal point from which the sun is traveling is quite near to Beta Columbae. So swift is this motion, nearly 20 kilometers per second, that it has provided a baseline of exceptional length, and very great service in determining the average distance of stars in groups or classes. After thousands of years, the sun's own motion combined with the proper motions of the stars will displace many stars appreciably from their familiar places. The constellations as we know them will suffer slight distortions, particularly Orion, Cassiopeia, and Ursa Major. Identity, or otherwise, of spectra often indicates what stars are associated together in groups, and their community of motion is known as star drift. Recent investigation of vast numbers of stars by both these methods have led to the epochal discovery of star streaming, which indicates that the stars of our system are drifting by, or rather through, each other in two stately and interpenetrating streams. The grand primary cause underlying this motion is as yet only surmised. End of chapter 46. Chapter 47 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in December 2021. Astronomy, the Science of the Heavenly Bodies by David Todd. Chapter 47. Stars and their Spectral Type. When in 1872 Dr. Henry Draper placed a very small wet plate in the camera of his spectroscope and, by careful following, on account of the necessarily long exposure, secured the first photographic spectrum of a star ever taken, he could hardly have anticipated the wealth of the new field of research which he was opening. His wife, Anna Palmer Draper, was his enthusiastic assistant in both laboratory and observatory, and on his death in 1882, she began to devote her resources very considerably to the amplification of stellar spectrum photography. At first, with the cooperation of Professor Young of Princeton, and later through extension of the facilities of Harvard College Observatory, whose director, the late Professor Edward C. Pickering, devoted his energies in very large part to this matter, all the preliminaries of the great enterprise were worked out, and a comprehensive program was embarked upon, which culminated in the Henry Draper Memorial, a catalogue and classification of the spectra of all the stars brighter than the 9th magnitude in both the northern and southern hemispheres. One very remarkable result from the investigation of large numbers of stars, according to their type, is the close correlation between a star's luminosity and its spectral type. But even more remarkable is the connection between spectral type and speed of motion. As early as 1892, Monk of Dublin, later Kapteyn, and still later Dyson, directed attention to the fact that stars of the Secchi type 2 had on the average larger proper motions than those of type 1. In 1903, Frost and Adams brought out the exceptional character of the Orion stars, the radial velocities of 20 of which averaged only 7 kilometers per second. Soon after, with the introduction of the two-stream hypothesis, a wider generalization was reached by Campbell and Kapteyn, whose radial velocities showed that the average linear velocity increases continually through the entire series B, A, F, G, K, M, from the earliest types of evolution to the latest. The younger stars of early type have velocities of perhaps 5 or 6 kilometers per second, while the older stars of later type have velocities nearly fourfold greater. The great question that occurs at once is, how do the individual stars get their motions? The farther back we go in a star's life history, the smaller we find its velocity to be. When a star reaches the Orion stage of development, its velocity is only 1/3 of what it may be expected to have finally. Apparently, then, the stars at birth have no motion, but gradually acquire it in passing through their several types or stages of development. More striking still is the motion of the planetary nebulae in excess of 25 kilometers per second, while type A stars move 11 kilometers, type G 15 kilometers, and type M 17 kilometers per second. Can the law connecting speed of motion and spectral type be so general that the planetary nebula is to be regarded as the final evolutionary stage? Stars have been seen to become nebulae, and one astronomer at least is strongly of the opinion that a single such instance ought to outweigh all speculation to the contrary, as that stars originate from nebulae. In his discussion of stellar proper motions, Boss has reached a striking confirmation of the relation of speed to type, finding for the cross-linear motion of the different types a series of velocities closely paralleling those of Kapteyn and Campbell. Concerning the marked relation of the luminosities of the stars to their spectral types, there is a pronounced tendency toward equality of brightness among stars of a given type. Also, the brightness diminishes very markedly with advance in the stage of evolution. There has been much discussion as to the order of evolution as related to the type of spectrum, and Russell of Princeton has put forward the hypothesis of giant stars and dwarf stars, each spectral type having these two divisions, though not closely related. One class embraces intensely luminous stars, the other stars only feebly luminous. When a star is in process of contraction from a diffused gaseous mass, its temperature rises, according to Lane's law, until that density is reached where the loss of heat by radiation exceeds the rise in temperature due to conversion of gravitational energy into heat. Then the star begins to cool again. So that if the spectrum of a star depends mainly on the effective temperature of the body, clearly the classification of the Draper catalogue would group stars together which are nearly alike in temperature, taking no note as to whether their present temperature is rising or falling. Another classification of stars by Lockyer divides them according to ascending and descending temperatures. Russell's theory would assign the succession of evolutionary types in the order M1, K1, G1, F1, A1, B, A2, F2, G2, K2, M2, the subscript 1 referring to the giants and 2 to the dwarf stars. In large part, the weight of evidence would appear to favor the order of the Harvard classification, independently confirmed as it is by studies of stellar velocities, galactic distribution, and periods of binary stars, both spectroscopic and visual, where Campbell and Aiken find a marked increase in length of period with advance in spectral type. At the same time, a vast amount of evidence is accumulating in support of Russell's theory. Investigations in progress will doubtless reveal the ground on which both may be harmonized. The publication of the new Henry Draper catalogue of stellar spectra is in progress, a work of vast magnitude. The great catalogue of 30 years ago embraced the spectra of more than 10,000 stars and was a huge work for that day. But the new catalogue utterly dwarfs it, with a classification much more detailed than in the earlier work, and with the number of stars increased more than 20-fold. This work, projected by the late director of the Harvard Observatory, has been brought to a conclusion by the energy and enthusiasm of Miss Annie J. Cannon through 6 years of close application, aided by many assistants. The catalogue ranges over the stars of both hemispheres, and is a monument to masterly organization and completed execution, which will be of the highest importance and usefulness in all future researches on the body of the stellar universe. End of chapter 47.
Chapter 48 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Krista Zaleski. Astronomy, the Science of the Heavenly Bodies by David Todd. Chapter 48. Star Distances. So vast are the distances of the stars that all attempts of the early astronomers to ascertain them necessarily proved futile. This led many astronomers after Copernicus to reject his doctrine of the Earth's motion round the sun, so that they clung rather to the Ptolemaic view that the Earth was without motion and was the center about which all the celestial motions took place. The geometry of stellar distances was perfectly understood, and many were the attempts made to find the parallaxes and distances of the stars. But the art of instrument making had not yet advanced to a stage where astronomers had the mechanisms that were absolutely necessary to measure very small angles. About 1835, Bessel undertook the work of determining stellar parallax in earnest. His instrument was the heliometer, originally designed for measuring the sun's diameter, but as modified for parallax work, it is the most accurate of all angle measuring instruments that the astronomers employ. The star that he selected was 61 Cygni, not a bright star of the 6th magnitude only, but its large proper motion suggested that it might be one of those nearest to us. He measured with the heliometer, at opposite seasons of the year, the distance of 61 Cygni from another and very small star in the same field of view, and thus determined the relative parallax of the two stars. The assumption was made that the very faint star was very much more distant than the bright one, and this assumption will usually turn out to be sound. Bessel got 0 seconds .35 for his parallax of 61 Cygni, and Struve, by applying the same method to Alpha Lyrae about the same time, got 0 seconds .25 for the parallax of that star. These classic researches of Bessel and Struve are the most important in the history of star distances, because they were the first to prove that stellar parallax, although minute, could nevertheless be actually measured. About the same time, success was achieved in another quarter, and Henderson, the British astronomer at the Cape of Good Hope, found a parallax of nearly a whole second for the bright star Alpha Centauri. Although the parallaxes of many hundreds of stars have been measured since, and the parallaxes of other thousands of stars estimated, the measured parallax of Alpha Centauri, as later investigated by Elkin and Sir David Gill, and found to be 0 seconds .75, is the largest known parallax, and therefore Alpha Centauri is our nearest neighbor among the stars so far as we yet know. This star is a binary system, and the light of the two components together is about the same as that of Capella, Alpha Aurigae, but it is never visible from this part of the world, being in 60 degrees of south declination. One might just glimpse it near the southern horizon from Key West. How the distances of the stars are found is not difficult to explain, although the method of doing it involves a good deal of complication, interesting to the practical astronomer only. Recall the method of getting the moon's distance from the Earth. It was done by measuring her displacement among the stars, as seen from two widely separated observatories, as near the ends of a diameter of the Earth as convenient. This is the baseline, and the angle which a radius of the Earth as seen from the center of the moon fills, or subtends, is the moon's parallax. So near is the moon that this angle is almost an entire degree, and therefore not at all difficult to measure. But if we go to the distance of even Alpha Centauri, the nearest of the stars, our Earth shrinks to invisibility, so that we must seek a longer baseline. Fortunately, there is one, but although its length is 25,000 times the Earth's diameter, it is only just long enough to make the star distances measurable. We found that the Sun's distance from the Earth was 93 million miles. The diameter of the Earth's orbit is therefore double that amount. Now conceive the diameter of the Earth replaced by the diameter of the Earth's orbit. By our motion round the Sun, we are transported from one extremity of this diameter to the opposite one in 6 months' time. So we may measure the displacement of a star from these two extremities, and half this displacement will be the star's parallax, often called the annual parallax, because a year is consumed in traversing its period. And it is this very minute angle which Bessel and Struve were the first to measure with certainty, and which Henderson found to be, in the case of Alpha Centauri, the largest yet known. Evidently, the Earth by its motion round the Sun makes every star describe a little parallactic ellipse. The nearer the star is, the larger this ellipse will be, and the farther the star, the smaller. If the star were at an infinite distance, its ellipse would become a point. That is, if we imagine ourselves occupying the position of the star, even the vast orbit of the Earth, 186 million miles across, would shrink to invisibility or become a mathematical point. Measurement of stellar parallax is one of many problems of exceeding difficulty that confront the practical astronomer. But the actual research nowadays is greatly simplified by photography, which enables the astronomer to select times when the air is not only clear, but very steady for making the exposures. Development and measurement of the plates can then be done at any time. Pritchard of Oxford, England, was among the earliest to appreciate the advantages of photography in parallax work, and Schlesinger, Mitchell, Miller, Slocum, and Van Man, with many others in this country, have zealously prosecuted it. How shall we intelligently express the vast distances at which the stars are removed from us? Of course we can use miles, and pile up the millions upon millions by adding on ciphers, but that fails to give much notion of the star's distance. Let us try with Alpha Centauri. Its parallax of 0 seconds 0.75 means that it is 275,000 times farther from the Sun than the Earth is. Multiplying this out, we get 25 trillion miles. That is 25 millions of million miles. An inconceivable number and an unthinkable distance. Suppose the entire solar system to shrink so that the orbit of Neptune, 60 times 93 million miles in diameter, would be a circle the size of the dot over this letter I. On the same scale, the Sun itself, although nearly 1 million miles in diameter, could not be seen with the most powerful microscope in existence. And on the same scale also, we should have to have a circle 10 feet in diameter if the solar system were imagined at its center and Alpha Centauri in its circumference. So astronomers do not often use the mile as a yardstick of stellar distance, any more than we state the distance from London to San Francisco in feet or inches. By convention of astronomers, the average distance between the centers of Sun and Earth, or 93 million miles, is the accepted unit of measure in the solar system. So, the adopted unit of stellar distance is the distance traveled by a wave of light in a year's time, and this unit is technically called the light year. This unit of distance, or stellar yardstick as we may call it, is nearly 6 millions of million miles in length. Alpha Centauri, then, is 4 1/3 light years distant, and 61 Cygni, 7 1/5 light years away. For convenience in their calculations, most astronomers now use a longer unit called the parsec, first suggested by Turner. Its length is equal to the distance of a star whose parallax is 1 second of arc. That is, 1 parsec is equal to about 3 1/4 light years. Or the light year is equal to 0.31 parsec. Also, the parsec is equal to 206,000 astronomical units, or about 19 millions of million miles. We have then 4 distinct methods of stating distance of a star. Sirius, for example, has a parallax of 0 seconds 0.38, or its distance is 2 2/3 parsecs, or 8 1/2 light years, or 50 millions of million miles. It is the angle of parallax which is always found first by actual measurement, and from this the other 3 estimates of distance are calculated. So difficult and delicate is the determination of a stellar distance that only a few hundred parallaxes have been ascertained in the past century. The distance of the same star has been many times measured by different astronomers, with much seeming duplication of effort. Comprehensive campaigns for determining star parallaxes in large numbers have been undertaken in a few instances, particularly at the suggestion of Kapteyn, an eminent astronomer of Groningen, Holland. His catalogue of star parallaxes is the most complete and accurate yet published, and is the standard in all statistical investigations of the stars. That we find relatively large parallaxes for some of the fainter stars, and almost no measurable parallax for some of the very bright stars, is one of the riddles of the stellar universe. We may instance Arcturus in the northern hemisphere and Canopus in the southern, the latter almost as bright as Sirius. Dr. Elkin and the late Sir David Gill determined exhaustively the parallax of Canopus, and found it very minute, only 0 seconds 0.03, making its distance in excess of 100 light-years. The stupendous brilliancy of this star is apparent if we remember that the intensity of its light must vary inversely as the square of the distance, so that if Canopus were to be brought as near us as even 61 Cygni is, it would be 100-fold brighter than Sirius, the brightest of all the stars of the firmament. In researches upon the distribution of the more distant stars, the method of measuring parallaxes of individual stars fails completely, and the secular parallax, or parallactic motion of the stars, is employed instead. By parallactic motion is meant the apparent displacement in consequence of the solar motion, which is now known with great accuracy, and amounts to 19.5 kilometers per second. Even in a single year, then, the Sun's motion is twice the diameter of the Earth's orbit, so that in 100 or more years, a much longer baseline is available than in the usual types of observations for stellar parallax. If we ascertain the parallactic motion of a group of stars, then we can find their average distance. It is found, for example, that the mean parallax of stars of the 6th magnitude is 0 seconds 0.014. Also, the mean distances of stars thrown into classes according to their spectral type have been investigated by Boss, Kaptian, Campbell, and others. The complete intermingling of the two great star streams has been proved, too, by using the magnitude of the proper motions to measure the average distances of both streams. These come out essentially the same, so that the streaming cannot be due to mere chance relation in line of sight. Most unexpected and highly important is the discovery that the peculiar behavior of certain lines in the spectrum leads to a fixed relation between a star's spectrum and its absolute magnitude, which provides a new and very effective method of ascertaining stellar distances. By absolute magnitudes are meant the magnitudes the stars would appear to have if they were all at the same standard distance from Earth. Very satisfactory estimates of the distance of exceedingly remote objects have been made within recent years by this indirect method, which is especially applicable to spiral nebulae and globular clusters. The absolute magnitude of a star is inferred from the relative intensities of certain lines in its spectrum, so that the observed apparent magnitude at once enables us to calculate the distance of the star. Adams and Joy have recently determined the luminosities and parallaxes of 500 stars by this spectroscopic method. Of these stars, 360 have had their parallaxes previously measured, and the average difference between the spectroscopic and the trigonometric values of the parallax is only the very small angle 0 seconds 0.0037, a highly satisfactory verification. An indirect method, but a very simple one, and of the greatest value because it provides the key to stellar distances with the least possible calculation. And we can ascertain also the distances of whole classes of stars, too remote to be ascertained in any other way at present known. The problem of spectroscopic determinations of luminosity and parallax has been investigated at Mount Wilson with great thoroughness from all sides, the separate investigations checking each other. A definitive scale for the spectroscopic determination of absolute magnitudes has now been established, and the parallaxes and absolute magnitudes have already been derived for about 1,800 stars. End of chapter 48.
Chapter 49 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Cosmic T. Astronomy, the Science of the Heavenly Bodies by David Todd. The nearest stars. Of especial interest are the few stars that we know are the nearest to us, and a given table includes all those whose parallax is 0.20 of second of an arc or greater. There are 19 in all, and nearly half of them are binary systems. The radial motions given are relative to the Sun. The transverse velocities are formed by using the measured parallaxes to transform proper motion into linear measures. They are given by Eddington in his stellar moments. These stars are distant less than 5 parsecs, about 16 light years, from the Sun. So they make up the closest fringe of the stellar universe immediately surrounding our system. The large number of binary systems is quite remarkable. Why some stars are single and others double is not yet known. By the spectroscopic method, the proportion is not so large. Campbell, finding that about 1/4 of 1,600 stars examined are spectroscopic binaries, and Frost 2/5 to a half. The exceptional number of large velocities is very remarkable. The average transverse motion of the 19 stars is 50 kilometers per second, whereas 30 is about what would have been expected. As to star streams to which these nearest stars belong, 11 are in stream 1 and 8 in stream 2, in close accord with the 3:2 ratio given by the 6,000 stars of Boss's catalogue. We are not able, says Eddington, to detect any significant difference between the luminosities, spectra, or speed of the stars constituting the two streams. The thorough interpretation of the two star streams is well illustrated, since we find even in this small volume of space that members of both streams are mingled together in just about the average proportion. End of chapter 49. Chapter 50 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Cosmic T. Astronomy, the Science of the Heavenly Bodies by David Todd. Actual dimensions of the stars. We have seen that the distances of the stars from the solar system are immense beyond conception, and millions upon millions of them are probably forever beyond our power of ascertaining by direct measurement what their distance really is. After we had found the sun's distance and measured the angle filled by his disk, it was easy to calculate his actual size. This direct method, however, fails when we try to apply it to the stars, because their distances are so vast that no star's disk fills an angle of any appreciable size. And even if we try to get a disk with the highest magnifying powers of great telescope, our efforts end only in failure. There is indeed no instrumentally appreciable angle to measure. How then shall we ascertain the actual dimensions of the vast spheres which we know the stars actually are, as they exist in the remotest regions of space? Clearly by indirect methods only, and it must be said that astronomers have as yet no general method that yields very satisfactory results for stellar dimensions. The actual magnitude of the variable system of Algol, Beta Persei, is among the best known of all the stars, because the spectroscope measures the rate of approach and recession of Algol when its invisible satellite is in opposite parts of the orbit. The law of gravitation gives the mass of the star and the size of its orbit, and so the length of the eclipse gives the actual size of the dark eclipsing body. This figures out to be practically the same size as that of our Sun, while Algol's own diameter is rather larger, exceeding 1,000,000 miles. If we try to estimate sizes of the stars by their brightness merely, we are soon astray. Differences of brightness are due to difference of dimensions, of course, or of light-giving area. But differences of distance also affect the brightness, inversely as the squares of the distance, while differences of temperature and constitution affect in very marked degree the intrinsic brilliance of the light emitting surface of the star. There are big stars and little stars, stars relatively near to us and stars exceedingly remote, and stars highly incandescent as well as others feebly glowing. We have already shown how the angular diameters subtended by many of the stars have been estimated through the relation of surface brightness and spectral type. Antares and Betelgeuse appear to be the most inviting for investigation because their estimated angular diameters are about 1/20th of a second of arc. This is the way in which their direct measurement is being attempted. As early as 1890, Michelson of Chicago suggested the application of interference methods to the accurate measurement of very small angles, such as the diameters of the minor planets and the satellites of Jupiter and Saturn, as well as the arc distance between the components of double stars. Two portions of the object glass are used, as far apart as possible on the same diameter, and the interference fringes produced at the focus of the objective are then the subject of observation. These fringes form a series of equidistant interference bands, and are most distinct when the light comes from a source subtending an infinitesimal angle. If the object presents an appreciable angle, the visibility is less and may even become zero. Michelson tested this method on the satellites of Jupiter at the Lick Observatory in 1891 and showed its accuracy and practicability. Nevertheless, the method has not been taken up by astronomers until very recently at the Mount Wilson Observatory, where Anderson has applied it to the measurement of close double stars. It is found that, contrary to general expectation, the method gives excellent results. Even if the seeing is not the best, 2 on a scale of 10, for instance. To simplify the manipulation of the interferometer, a small plate with 2 apertures in it is placed in the converging beam of light coming from the telescope objective or mirror. The interference fringes formed in the focal plane are then viewed with an eyepiece of very high power, many thousand diameters. The resolving power of the interferometer is found to be somewhat more than double that of a telescope of the same aperture. By applying the interferometer method to Capella, arc distances of much less than 1/20th of a second of arc were measured. More recently, the method has been applied to the great star Betelgeuse in Orion, whose angular diameter was found to be 0.46 arc-second, corresponding to an actual diameter of 260 million miles, if the star's parallax is as small as it appears to be. End of chapter 50.
Chapter number 51 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Astronomy, the Science of the Heavenly Bodies by David Todd. The Variable Stars. Spectacular as they are to the layman, novae, or temporary stars, are to the astronomer simply a class among many thousands of stars which they call variables, or variable stars. There are a few objects classified as irregular variables, one of which is very remarkable. We refer to Eta Argus, an erratic variable in the southern constellation Argo and surrounded by a well-known nebula. There is a pretty complete record of this star. Halley, in 1677, when observing at St. Helena, recorded Eta Argus as of the 4th magnitude. During the 18th century, it fluctuated between the 4th magnitude and the 2nd. Early in the 19th, it rapidly waxed in brightness, fluctuating between the 1st and 2nd magnitudes from 1822 to 1836. But 2 years later, its light tripled, rivaling all the fixed stars except Canopus and Sirius. In 1843, it was even brighter for a few months, but since then it has declined fairly steadily, reaching a minimum at magnitude 7.5 in 1886, with a slight increase in brightness more recently. A period of half a century has been suggested, but it is very doubtful if Eta Argus has any regular period of variation. Another very interesting class of variables is known as the Omicron Ceti type. Nearly all the time they are very faint, but quite suddenly they brighten through several magnitudes and then fade away more or less slowly to their normal condition of faintness. But the extraordinary thing is that most of these variables go through their fluctuations in regular periods, from 6 months to 2 years in length. The type star, Omicron Ceti, or Mira, is the oldest known variable, having been discovered by Fabricius in 1596. Most of the time, it is a relatively faint star of the 12th magnitude, but once in rather less than a year, its brightness runs up to the 4th, 3rd, and sometimes even the 2nd magnitude, where it remains for a week or 10 days, and afterwards it recedes more slowly to its usual faintness, the entire rise and decline in brightness usually requiring about 100 days. The spectrum of Omicron Ceti contains many very bright lines, and a large proportion of the variable stars are of this type. Another class of variables is designated as the Beta Lyra type. Their periods are quite regular, but there are 2 or more maxima and minima of light in each period, as if the variation were caused by superposed relations in some way. Their spectra show a complexity of helium and hydrogen bands. No wholly satisfactory explanation has yet been offered. Probably they are double stars revolving in very small orbits compared with their dimensions, their plane of motion passing nearly through the Earth. But the most interesting of all the variables are those of the Algol type, their light curves being just the reverse of the Omicron Ceti type. That is, they are at their maximum brightness most of the time, and then suffer a partial eclipse for a relatively brief interval. Algol goes through its variations so frequently that its period is very accurately known. It is 2 days, 20 hours, 48 minutes, 55.4 seconds. For most of this period, Algol is an easy 2nd magnitude star. Then, in about 4.5 hours, it loses nearly 5/6 of its light, receding to the 4th magnitude. Here at minimum it remains for 15 or 20 minutes, and then in the next 3.5 hours it regains its full normal brilliancy of the 2nd magnitude. During these fluctuations, the star's spectrum undergoes no marked changes. The spectra of all the Algol variables are of the 1st or Sirian type. To explain the variation of the Algol type of variables is easy. A dark eclipsing body, somewhat smaller than the primary, is supposed to be traveling round it in an orbit lying nearly edgewise to our line of sight. The gravitation of this dark companion displaces Algol itself alternately toward and from the Earth, because the 2 bodies revolve round their common center of gravity. With the spectroscope, this alternate motion of Algol, now advancing and now receding at the rate of 26 miles per second, has been demonstrated, and the period of this motion synchronizes exactly with the period of the star's variability. Russell and Shapley have made extended studies of the eclipsing binaries and developed the formulae by which investigations of their orbits are conducted. Heretofore, visual binaries and spectroscopic binaries afforded the only means of deriving data regarding double systems, but it is now possible to obtain from the orbits of eclipsing variables fully as much information relating to binary systems in general and their bearing on stellar evolution. After an orbit has been determined from the photometric data of the light curve, the addition of spectroscopic data often permits the calculation of the masses, dimensions, and densities in terms of the Sun. Shapley's original investigation included the orbits of 90 eclipsing variables, and with the aid of hypothetical parallaxes, he computed the approximate position of each system in space. The relation to the Milky Way is interesting, the condensation into the galactic plane being very marked. Only 13 of the 90 systems being found at galactic latitudes exceeding 30 degrees. If we can suppose the variable stars covered with vast areas of spots, perhaps similar to the spots on the Sun, and then combine the variation of these spots areas with rotation of the star on its axis, there is a possibility of explanation of many of the observed phenomena, especially where the range of variation is small. But for the Omicron Ceti type, no better explanation offers than that afforded by Sir Norman Lockyer's collision theory. First, he assumes that these stars are not condensed bodies, but still in the condition of meteoric swarms, and the revolution of lesser swarms around larger aggregations. in elliptic orbits of greater or less eccentricity must produce vast multitudes of collisions, and these collisions, taking place at pretty regular periods, produce the variable maximum light by raising hosts of meteoric particles to a state of incandescence simultaneously. The catalogs of variable stars now contain many thousands of these objects. They are often designated by the letters R, S, T, and so on, followed by the genitive form of the name of the constellation wherein they are found. Most of the recently found variables have a range of less than 1 magnitude. They are so distributed as to be most numerous in a zone inclined about 18 degrees to the celestial equator and split in two near where the cleft in the galaxy is located. Nearly all the temporary stars are in this duplex region. Bailey of Harvard, a quarter-century ago, began the investigation of variables in closed star clusters, where they are very abundant, with marked changes of magnitude within only a few hours. Many amateur astronomers afford very great assistance to the professional investigator of variable stars by their cooperation in observing these interesting bodies. In particular, the American Association of Observers of Variable Stars, organized and directed by William Tyler Olcott. For a high degree of accuracy in determining stellar magnitudes, the photoelectric cell is unsurpassed. Stebbins of Urbana has been very successful in its application, and he discovered the secondary minimum of algol with the selenium cell. His most recent work was done with a potassium cell with walls of fused quartz, perfected after many trial attempts. The stars he has recently investigated are Lambda Tauri and Pi 5 Orionis. Combining results with those reached by the spectroscope, the masses of the two component stars of the former are 2.5 and 1.1 that of the Sun, and the radii are 4.8 and 3.6 times the Sun's. Russell of Princeton thinks it probable that similar causes are at work in all these variables. In the case of the typical novae, there is evidence that when the outburst takes place, a shell of incandescent gas is actually ejected by the star at a very high velocity. What may be the forces that cause such an explosion can only be guessed. Repeated outbursts have not, in the case of T. Pyxidus, destroyed the star, because it has gone through this process 3 times in the past 30 years. Russell inclines to regard it as a standard process occurring somewhere in the stellar universe, probably as often as once a year. Novae, then, cannot be due to collisions between two stars, for even if we suppose the stars to be 1,000 millions in number, no two should collide except at average intervals of many million years. The idea is gaining ground that the stars are vast storehouses of energy, which they are gradually transforming into heat and radiating into space. Quote, under ordinary circumstances, it is probable that the rate of generation of heat is automatically regulated to balance the loss by radiation. But it is quite conceivable that some sudden disturbance in the substance of the star near the surface might cause an abrupt liberation of a great amount of energy, sufficient to heat the surface excessively and drive the hot material off into infinite space, in much the form of a shell of gas, as seems to have been observed in the case of Novae Aquilae. With the rapid advance of our knowledge of the properties of the stars on one hand, and of the very nuclei of atoms on the other, we may, perhaps, before many years have passed, find ourselves nearer a solution of the problem. End quote. The Cepheid variables increase very rapidly in brightness from their least light to their maximum, and then fade out much more slowly, with certain irregularities or roughness of their light curves when declining. Their spectral lines also shift in period with their variations of light. In the case of these variables, whose regular fluctuation of light cannot be due to eclipse, and is as a rule embraced within a few days, there is a fluctuation in color also between maximum and minimum, as if there were a periodic change in the star's physical condition. Eddington and Shapley advocate the theory of a mechanical pulsation of the star as most plausible. Knowledge of the internal conditions of the stars make it possible to predict the period of pulsation within narrow limits. And for Delta Cephei, this theoretical period is between 4 and 10 days. Its observed period is 5 1/3 days, and corresponding agreement is found in all the Cepheids so far tested. Shapley of Mount Wilson finds that the Cepheid variables with periods exceeding a day in length all lie close to the galactic lane, So greatly have the studies of these objects progressed that, as before remarked, when we know the star's period, we can get its absolute magnitude, and from this, the star's distance. On all sides of the Sun, the distances of the Cepheids range up to 4,000 parsecs, so they indicate the existence of a galactic system far greater in extent than any previously dealt with. End of Chapter 51. Read by Susie Vera in the city of Los Angeles, February 1st, 2022.
Chapter 52 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Krista Zaleski. Astronomy, the Science of the Heavenly Bodies by David Todd. Chapter 52. The Novae, or New Stars. New stars, or temporary stars, we have already mentioned in connection with variables. They are, next to comets, the most dramatic objects in the heavens. They may be variable stars which, in a brief period, increase enormously in brightness and then slowly wane and disappear entirely, or remain of a very faint stellar magnitude. In the ancient historical records are found accounts of several such stars. For instance, in the Chinese annals there is an allusion to such a stellar outburst in the constellation of Scorpio, BC 134. This was observed also by Hipparchus, and no doubt it was the immediate incentive which led to his construction of the first known catalogue of stars, so that similar happenings might be detected in the future. In November 1572, Tycho Brahe observed the most famous of all new stars, which blazed out in the constellation Cassiopeia. In something over a year, it had completely disappeared. In 1604 to 1605, a new star of equal brightness was seen in Ophiuchus by Kepler. It also faded out to invisibility in 1606. Kepler and Tycho printed very complete records of these remarkable objects. The 18th century passed without any new stars being seen or recorded. There was one of the 5th magnitude in 1848, and another of the 7th magnitude in 1860, and in May 1866, a star of the 2nd magnitude suddenly made its appearance in Corona Borealis, and one of the 3rd magnitude in Cygnus in November 1876. The latter was fully observed by Schmidt of Athens, and became a faint telescopic star within a few weeks. It is now of the 15th magnitude. In 1885, astronomers were surprised to find suddenly a new star of the 6th magnitude very close to the brightest part of the great nebula in Andromeda. It ran its course in about 6 months, fading with many fluctuations in brightness, and no star is now visible in its position, even with the telescope. Stars of this class are known to astronomers as novae, usually with the genitive of the constellation name, as Nova Andromedae. In 1891 to 1892, Nova Aurigae made its spectacular appearance and yielded a distinctly double and complex spectrum for more than a month. Many pairs of lines indicated a community of origin as to substance, and accurate measurement showed a large displacement with a relative velocity of more than 500 miles per second. For each bright hydrogen line displaced toward the red, there was a dark companion line, or band about equally displaced toward the violet, much as if the weird light of Nova Aurigae originated in a solid globe, moving swiftly away from us and plunging into an irregular nebulous mass as swiftly approaching us. Parallax observations of Nova Aurigae made it immensely remote, perhaps within the galaxy, and it still exists as a faint nebulous star. In February 1901, in the constellation Perseus appeared the most brilliant nova of recent years. It was first discovered by Dr. Anderson, an amateur of Glasgow, and at maximum on February 23rd it outshone Capella. There were many unusual fluctuations in its waning brightness. Its spectrum closely resembled that of Nova Aurigae, with calcium, helium, and hydrogen lines. In August 1901, an enveloping nebula was discovered, and a month later certain wisps of this nebulosity appeared to have moved bodily, at a speed 70-fold greater than ever previously observed in the stellar universe. According to Sir Norman Lockyer's meteoritic hypothesis, A vast nebulous region was invaded, not by one but by many meteor swarms, under conditions such that the effects of collision varied greatly in intensity. The most violent of these collisions gave birth to Nova Persei itself, and the least violent occurred subsequently in other parts of the disturbed nebula, perhaps immeasurably removed. This explanation would avoid the necessity of supposing actual motion of matter through space at velocities heretofore unobserved and inconceivably high. A recent photograph of Nova Persei by Ritchie reveals a nebulous ring of regular structure surrounding the star. The great power of the 60-inch has made it possible to photograph even the spectra of many of the novae of years ago, which are now very faint. After the lapse of years, the characteristic lines of the nebular spectrum generally vanish, as if the star had passed out of the nebula, a plunge into which is generally thought to be the cause of the great and sudden outburst of light. Many novae have recently been found in the spiral nebulae, especially in the great nebula of Andromeda. End of chapter 52.
Chapter 53 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Cosmic T. Astronomy, the Science of the Heavenly Bodies by David Todd. The double stars. Examining individual stars of the heavens more in detail, thousands of them are found to be double, not the stars that appear double to the naked eye, as Theta Tauri, Mizar, Epsilon Lyrae, and others, but pairs of stars much closer together and requiring the power of the telescope to divide or separate them. Only a very few seconds apart they are, or in many cases only the merest fraction of a second apart. Some of them, called binaries, are found to be revolving around a common center, sometimes in only a few years, sometimes in stately period of hundreds of years. Many such binary systems are now known, and the number is constantly increasing. Castor is one, Gamma Virgin is another, Sirius is also one of these binaries, and a most interesting one, having a period of revolution of about 52 years. Aitken of the Lick Observatory, in his work on binary stars, directs special attention to the correlation between the elements of known binary orbits and the star's spectral type, and presents a statistical study of the distribution of 54,000 visual double stars, of which the spectra of 3,919 are known. That the masses of binary systems average about twice that of the Sun's mass has long been known, and this fact can be employed with confidence in estimates of the probable parallax of these systems. Aitken applies the test to 14 visual systems for which the necessary data are available, and deduces for them a mean mass of 1.76 times that of the Sun. For the spectroscopic binaries, the masses are much greater. Triple, quadruple, and multiple stars are less frequent, but many exceedingly interesting objects of this class exist. Epsilon Lyrae is one, a double-double of 4 stars as seen with slender telescopic power, and 6 or 7 stars with larger instruments. Sigma Orionis and 12 Lynces, also Theta Cancri and Mu Boötis, are good examples of triple stars. End of chapter 53.
Chapter 54 of Astronomy, the Science of Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Astronomy, the Science of Heavenly Bodies by David Todd. The Star Clusters. From multiple stars, the transition is natural to star clusters, although the gap between these types of stellar objects is very broad. The familiar group of the winter sky, known as the Pleiades, is a loose cluster, showing relatively very few stars even in telescopes or on photographic plates. The Beehive, or cluster known as Praesepe in Cancer, and a double group in the sword handle of Perseus, both just visible to the naked eye, are excellent examples of star clusters of the average type. When the moon is absent, they are easily recognized without a telescope as little patches of nebulous light, but every increase of optical power adds to their magnificence. Then we come in regular succession to the truly marvelous globular clusters, that for instance in Hercules. Messier 13, a recent photograph of which taken by Ritchie with the 60-inch reflector on Mount Wilson, reveals an aggregation of more than 50,000 stars. But the finest specimens are in the southern hemisphere. Sir John Herschel spent much time investigating them nearly a century ago at the Cape of Good Hope. His description of the cluster in the constellation of Centaurus is as follows. The noble globular cluster Omega Centauri is beyond all comparison the richest and largest object of the kind in the heavens. The stars are literally innumerable, and as their total light when received by the naked eye affects it hardly more than a star of the 5th or 4th to 5th magnitude, the minuteness of each star may be imagined. Others of these clusters are so remote that the separate stars are not distinguishable, especially at the center, and their distances are entirely beyond our present powers of direct measurement, although methods of estimating them are in process of development. If gravitation is regnant among these uncounted components of stellar clusters, as doubtless it is, these stars must be in rapid motion, although our photographs of measurements have been made too recently for us to detect even the slightest motion in any of the component stars of a cluster. The only variations are changes of apparent magnitude, of a first type detected in a large number of stars in Omega Centauri by Bailey of Harvard, who, by comparison of photographs of the globular clusters, was the first to find variable stars quite numerous in the objects. There unexplained variations of magnitude take place with great rapidity, often within a few hours. There are about 100 of these globular clusters, and the radial velocities of 10 of them have been measured by Slipher and found to range from a recession of 410 to an approach of 225 kilometers per second. These excessive velocities are comparable with those found for the spiral nebulae. Shapley has estimated the distances of many of these bodies, which contain a large number of variable stars of the Cepheid type. By assuming their absolute magnitudes equal to those of similar Cepheids at known distances, he finds their distance represented by the inconceivably minute parallax of 0 inches .00012, corresponding to 30,000 light years. This research also places the globular clusters far outside and independent of our galactic system of stars. The distribution of globular clusters has also been investigated, and these interesting objects are found almost exclusively in but one hemisphere of the sky. Its center lies in the rich star clouds of Scorpio and Sagittarius. Success in finding the distances of these objects has made it possible to form a general idea of their distribution in three-dimensional space. The numerous variable stars in any one cluster are remarkable for their uniformity. Accepting variables of this type as a constant standard of absolute brightness, and assuming that the differences of average magnitude of the variables in different clusters are entirely due to differences of distance, the relative distances of many clusters were ascertained with considerable accuracy. Then it was found that the average absolute magnitude of the 25 brightest stars in a cluster is also a uniform standard, or about 1.3 magnitudes brighter than the mean magnitude of the variables. This new standard was employed in ascertaining the distances of other clusters not containing many variables. Shapley further shows that the linear dimensions of the clusters are nearly uniform, and the proper relative positions in space are charted for 69 of these objects. We can determine the scale of the charts if we know the absolute brightness of our primary standard, the variable stars, and this is deduced from a knowledge of the distance of variables of the same type in our immediate stellar system. The most striking of all the globular clusters, Omega Centauri, comes out the nearest. Nevertheless, it is a distant 6.5 kiloparsecs. A kiloparsec is 1,000 parsecs, and is the equivalent of 3,256 light-years. At the inconceivable distance of 67 kiloparsecs, or more than 200,000 light-years, is the most remote of the globular clusters, known to astronomers as NGC 7006. From its number in the catalogue which records its position in the sky, the New General Catalogue of Nebulae by Dreyer of Armagh. The clusters are widely scattered, and their center of diffusion is about 20 kiloparsecs on the galactic plane toward the region of Scorpio-Sagittarius. Marked symmetry with reference to this plane makes it evident that the entire system of globular clusters is associated with the galaxy itself. But to conceive of this, it is necessary to extend our ideas of the actual dimensions of the galactic system. Almost on the circumference of the great system of globular clusters, our local stellar system is found, and it contains probably all the naked eye stars, with millions of fainter ones. Its size seems almost diminutive, only about 1 kiloparsec in diameter. The relative location of our local stellar system shows why the globular clusters appear to be crowded into one hemisphere only. Shapley suggests that globular clusters can exist only in empty space, and that when they enter regions of space tenanted by other stars, they dissolve into the well-known loose clusters and the star clouds of the Milky Way. Strangely, the radial velocities of the clusters already observed show that most of them are traveling toward this region, and that some will enter the stellar regions within a period of the order of 100 million years. The actual dimensions of globular clusters are not easy to determine, because the outer stars are much scattered. To a typical cluster, Messier 3, Shapley assigns a diameter of 150 parsecs, which makes it comparable with the size of the stellar cluster to which the Sun belongs. Also, on certain likely assumptions, he finds that the diameter of the great cluster in Hercules, the finest one in our northern sky, is about 350 parsecs, and its distance no less than 30,000 parsecs. In other words, the staggering distance that light would require 9,750,000 years to travel over. While these distances can never be verified by direct measurement, it lends great weight to the three methods of indirect measurement, or estimation. 1. From the diameter of the image of the clusters. 2. From the mean magnitude of the 25 brightest stars. And 3. From the mean magnitude of the short period variables, that they are in excellent agreement. End of chapter 54.
Chapter 55 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Trek. Astronomy, the Science of the Heavenly Bodies by David Todd. Moving Clusters. Recent researches on the proper motions of stars have brought to light many groups of stars whose individual members have equal and parallel velocities. Eddington calls these moving clusters. The component stars are not exceptionally near to each other, and it often happens that other stars not belonging to the group are actually interspersed among them. They may be likened to double stars, which are permanent neighbors with some orbital motion, though exceedingly slow. The connection is rather one of origin, occurring in the same region of space, perhaps from a single nebula. They set out with the same motion and have shared all the accidents of the journey together. Their equality of motion is intact because any possible deflections by the gravitative pull of the stellar system is the same for both. Mutual attraction may tend to keep the stars together, but their community of motion persists chiefly because no forces tend to interfere with it. In this way, physically connected pairs may be separated by very great distances. So, with the moving clusters, their component stars may be widely separate on the celestial sphere, but equality of their motion affords a clue to their association in groups. The Hyades, a loose cluster in Taurus, is a group of 39 stars within an area of about 15 degrees square, which has been pretty fully investigated, especially by the late Professor Louis Boss, and no doubt many fainter stars in the same region will ultimately be found to belong to the same group. If we draw arrows on a chart representing the amount and direction of the proper motions of these stars, these arrows must all converge toward a point. This shows that their motions are parallel in space. It is a relatively compact group, and their close convergence shows that their individual velocities must agree within a small fraction of a kilometer per second. Radial velocity measures of 6 of the component stars are in very satisfactory accord, giving 45.6 kilometers per second for the entire group. We can get the transverse velocity and therefrom the distances of the stars, which are among the best known in the heavens, because the proper motions are very accurately known. The mean parallax of the group by this indirect method comes out to be 0.25 arc seconds, agreeing almost exactly with the direct determination by photography as 0.23 arc seconds by Captain, De Sitter, and others. Eddington concludes that this Taurus group is a globular cluster with a slight central condensation. Its entire diameter is 10 parsecs and its known motion enables us to trace its past and future history. It was nearest the Sun 8 lakhs years ago when it was about half its present distance. Boss calculated that in 65 million years, if the present motion is maintained, this group will have receded so far as to appear like an ordinary globular cluster 20 feet in diameter, its stars ranging from the 9th to the 12th apparent magnitude. We may infer that the motion will likely continue undisturbed because there are interspersed among the groups many stars not belonging to it, and these have neither scattered its members nor sensibly interfered with the parallelism of their motion. Another moving cluster, the similarity of proper motion of whose component stars was first pointed out by Proctor, is known as the Ursa Major system, which embraces primarily Beta, Gamma, Delta, Epsilon, and Zeta Ursae Majoris, or 5 of the 7 stars that mark the familiar Dipper. But as many as 8 other stars widely scattered are thought to belong to the same system, including Sirius and Alpha Coronae Borealis. The absolute motion amounts to 28.8 kilometers per second and is approximately parallel to the galaxy. Turner has made a model of the cluster which has the form of a flat disk. Among stars of the Orion type of a spectrum are several examples of moving clusters. The Pleiades, together with many fainter stars from another moving cluster, as also do the brighter stars of Orion, together with the faint cloud-like extensions of the Great Nebula in Orion, whose radial velocity agrees with that of the stars in the constellation. Still, another very remarkable moving cluster is in Perseus, first detected by Eddington and embracing 18 stars, the brightest of which is Alpha Persei. The further discovery of moving clusters is most important in the future development of stellar astronomy, because with their aid we can find out the relative distribution, luminosity, and distance of very remote stars. So far, the stars found associated in groups are of early types of a spectrum, but the Taurus clusters embraces several members equally advanced in evolution with the Sun. And in the more scattered system of Ursae Major, there are 3 stars of type F. Some of these systems, Eddington concludes, would thus appear to have existed for a time comparable with the lifetime of an average star. They are wandering through a part of space in which are scattered stars not belonging to their system interlopers penetrating right among the cluster stars. Nevertheless, the equality of motion has not been seriously disturbed. It is scarcely possible to avoid the conclusion that the chance attractions of stars passing in the vicinity have no appreciable effect on stellar motion, and that if the motions change in course of time, as it appears they must do, this change is due not to the passage of individual stars but to the central attraction of the whole stellar universe, which is sensibly constant over the volume of space occupied by a moving cluster. End of section 55.
Chapter 56 of Astronomy, the Science of Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Astronomy, the Science of Heavenly Bodies, by David Todd. The Two Star Streams. Consider the ships on the Atlantic voyaging between Europe and America. At any one time there may be 100 or more, all bound either east or west, some moving in interpenetrating groups, individuals frequently passing each other, but rarely or never colliding. We might say there are two great streams of ships, one moving east and the other west. Now, in place of each ship, imagine 100 ships, and magnify their distances from each other to the vast distances that the stars are from each other, and all in motion in two great streams as before. This will convey some idea of the relatively recent discovery called by astronomers star streaming. Early in this century, the investigation of moving clusters began to reveal the fact that the motions of the stars were not at random throughout the universe, and about 1904 Captain was the first to show that the stellar motions considered in great groups are very far from being haphazard, but that the stars tend to travel in two great streams, or favored directions. This was ascertained by analyzing the proper motions of stars in the sky, many thousands of them, and correcting all for the effect which the known motion of the sun would have upon them. The corrected motion, or part that is left over, is known as the star's own motion, or modus peculiaris. This important investigation was greatly facilitated by the general catalogue of 6,188 stars well distributed over the entire sky, the work of the late Professor Boss. It was published by the Carnegie Institution of Washington and includes all stars down to the 6th magnitude. Boss was very critical in the matter of stellar positions and proper motions, and his work is the most accurate at present available. Excluding stars of the Orion type and the known members of moving clusters, Captain's investigation was based on 5,322 stars, which he divided into 17 regions of the sky, each northern region having an antipodal one in the southern hemisphere. Mathematical analysis of these regions showed them all in substantial agreement, with one exception, and enabled Captain to draw the conclusion that the stars of one stream, called drift 1, move with a speed of 32 kilometers per second, while those of the other, drift 2, travel with a speed of 18 kilometers per second. Their directions are not, like those of the east and west bound ships, 180 degrees from each other, but are inclined at an angle of 100 degrees. Mathematical analysis of these regions showed them all in substantial agreement, with one exception, and enabled Captain to draw the conclusion that the stars of one stream, called drift 1, move with a speed of 32 kilometers per second, while those of the other, drift 2, travel with a speed of 18 kilometers per second. Their directions are not, like those of east and west bound ships, 180 degrees from each other, but are inclined at an angle of 100 degrees. Drift 1 embraces about 3/5 of the stars, and drift 2 the remaining 2/5. Quite as remarkable as the drift themselves is the fact that the relative motion of the two is very closely parallel to the plane of the Milky Way. This epochal research has very great significance in all investigations of stellar motions, and it has been verified in various ways, particularly by the Astronomer Royal, Sir Frank Dyson, who limited the stars under consideration to 1,924 in number, but all having very large proper motions. In this way, the two streams are even more characteristically marked. But radial velocity determinations afford the ultimate and most satisfactory test, and Campbell has this investigation in hand, classifying the stars in their streaming according to this type. Type A stars are so far found to be confirmatory. Turning to the question of physical differences between the stars of the two streams, Eddington inquires into the average magnitude of the stars in both drifts, and their spectral type. Also whether they are distributed at the same distance from the sun and in the same proportion in all parts of the sky. His conclusion is that there is no important difference in the magnitudes of the stars constituting the two drifts. Regarding their spectra, stars of early and late types are found in both streams, and a somewhat higher proportion of late types among the stars of drift 2 than those of drift 1. Campbell and Moore of the Lick Observatory have investigated 73 planetary nebulae which exhibit the phenomena of star streaming, and have motions which are characteristic of the stars. Dealing with the very important question whether the two streams are actually intermingled in space, Eddington finds them nearly at the same mean distance and thoroughly intermingled, and there is no possible hypothesis of drifts 1 and 2 passing one behind the other in the same line of sight. A third drift, to which all the Orion stars belong, is under investigation, together with comprehensive analysis of the drifts according to their spectral type of all the stars included. The farther research on star streaming is pushed, the more it becomes evident that a third stream, called drift O, is necessary, especially to include B-type stars. The farther we recede from the sun, the more this drift is in evidence. At the average distances of B-type stars, the observed motions are almost completely represented by drift O alone. Halm of Cape Town concludes from recent investigations that the double drift phenomena, drifts 1 and 2, is of a distinctly local character, and concerns chiefly the stars in the vicinity of the solar system, while stars in the greatest distances from the sun belong preeminently to drift O. The 60-inch reflector on Mount Wilson gathers sufficient light so that the spectra of very faint stars can be photographed, and a discussion of velocities derived in this manner has shown that Captain's two-star streams extend into space much farther than it was possible to trace them with the nearer stars. Star streaming, then, may be a phenomenon in the widest significance in reference to the entire universe. As to the fundamental cause for the two opposite and nearly equal star streams, it is early perhaps to even theorize upon the subject. Eddington, however, finds a possible explanation in the spiral nebulae, which are so numerous as to indicate the certainty of an almost universal law compelling matter to flow in these forms. Why it does so we cannot be said to know, but obviously matter is either flowing into the nucleus from the branches of the spiral, or it is flowing out from the nucleus into the branches. Which of the two directions does not matter, because in either case there would be currents of matter in opposite directions at the points where the arms merge in the central aggregation. The currents continue through the center, because the stars do not interfere with one another's paths. As Eddington concludes, there, then, we have an explanation of the prevalence of motions to and fro in a particular straight line. It is the line from which the spiral branches start out. The two-star streams and the double-branch spirals arise from the same cause. End of chapter 56.
Chapter 57 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. Astronomy, the Science of the Heavenly Bodies by David Todd. The Galaxy or Milky Way. grandest of all the problems that have occupied the mind of man is the distribution of the stars throughout space. To the earliest astronomers who knew nothing about the distances of the stars, it was not much of a problem because they thought all the fixed stars were attached to a revolving sphere and therefore all at essentially the same distance, a very moderate distance too. Even Kepler held the idea that the distances of individual stars from each other are much less than their distances from our Sun. Thomas Wright of Durham, England, seems to have been the first to suggest the modern theory of the structure of the stellar universe about the middle of the 18th century. His idea was taken up by Kant, who elaborated it more fully. It is founded on the galaxy, the basal plane of the stellar distribution, just as the ecliptic is the fundamental circle of the reference in the solar system. What is the galaxy or Milky Way? Here is the great poet's view of the most poetic object in all nature. A broad and ample road, whose dust is gold, and pavement stars, as stars to thee appear, seen in the galaxy that Milky Way, which nightly as a circling zone thou seest, powdered with stars. Milton P.L. 7, 580. Were the earth transparent as crystal, so that we could see downward through it and outward in all directions to the celestial sphere, the galaxy or Milky Way would appear as a belt or zone of cloud-like luminosity extending all the way round the heavens. As the horizon cuts the celestial sphere in two, we see at any one time only one half of the Milky Way, spanning the dome of the sky as a cloud-like arc. As the general plane of the galaxy makes a large angle with our equator, the Milky Way is continually changing its angle with the horizon, so that it rises at different elevations. One half of the Milky Way will always be below our horizon, and a small region of it lies so near the south pole of the heavens that it can never be seen from medium northern latitudes. Galileo was the first to explain the fundamental mystery of this belt when he turned his telescope upon it and found that it was not a continuous sheet of faint light as it seemed to be, but was made up of countless numbers of stars, individually too faint to be visible to the naked eye, but whose vast number, taken in the aggregate, gave the well known effect which we see in the sky. In some regions, as Perseus, the stars are more numerous than in others, and they are gathered in close clusters. The larger the telescope we employ, the greater the number of stars that are seen as we approach the galaxy on either side, and the farther we recede from the galaxy and approach either of its poles, fewer and fewer stars are found. Indeed, if all the stars visible in a 12-inch telescope could be conceived as blotted out, nearly all the stars that are left would be found in the galaxy itself. The naked eye readily notes the variations in breadth and brightness of the galactic zone. Nearly a third of it, from Scorpio to Cygnus, it split into two divisions nearly parallel. In many regions, its light is interrupted, especially in Centaurus, where a dark starless region exists known as the coal sack. Sir John Herschel, who followed up the stellar researches of his father, Sir William, in great detail, places the north pole of the galactic plane in the declination of 37 degrees north and Right ascension 12 hours 47 minutes. This makes the plane of the Milky Way lie at an angle of about 60 degrees with the ecliptic, which it intersects not far from the solstices. Now Kant, in view of the two great facts about the galaxy known in his time, one, that it wholly encircles the heavens, and two, that it is composed of countless stars too faint to be individually visible to the naked eye, drew the safe conclusions that the system of the stars must extend much farther in the direction of Milky Way than in other directions. This theory of Kant was next investigated from an observational standpoint by Sir William Herschel, the ultimate goal of whose researches was always a knowledge of the construction of the heavens. The present conclusion is that we may regard the stellar bodies of the sidereal universe as scattered, without much regard to uniformity, throughout a vast space having in general the shape of a thick watch, its thickness being perhaps one-tenth its diameter. On both sides of this disk of stars, and clustered about the poles of the sidereal system, are the regions occupied by vast numbers of nebulae. The entire visible universe, then, would be spheroidal in general shape. The plane of the Milky Way passes through the middle of the aggregation of stars and nebulae, and the solar system is near the center of the Milky Way. Throughout the watch-form space, the stars are clustered irregularly in varied and sometimes fantastic forms, but without approach to order or system. If we accept some of the star groups and star clusters and consider only the naked eye stars, we find them scattered with fair approach to uniformity. The watch-shaped disk is not to be understood as representing the actual form of the stellar system, but only in general the limits within which it is for the most part contained. A vigorous attack on the problem of the evolution and structure of the stellar universe as a whole is now being conducted by cooperation of many observatories in both hemispheres. It is known as the Captain Plan of Selected Areas, embracing 206 regions which are distributed regularly over the entire sky. Besides this, a special plan includes 46 additional regions, either very rich or extremely poor in stars, or to which other interest attaches. Of all investigators, Captain has gone into the question of our precise location in the Milky Way most thoroughly, concluding that the solar system lies not at the center in the exact plane, but somewhat to the north of the galaxy. Discussing the Sirian stars, he finds that if stars of equal brightness are compared, the Sirians average nearly 3 times more distance from the Sun than those of the solar type. So probably the Sirians far exceed the solars in intrinsic brightness. Further, Captain concludes that the galaxy has no connection with our solar system and is composed of a vast encircling annulus or ring of stars, far exceeding in number of stars of the great central solar cluster and everywhere exceedingly remote from these stars, as well as differing from them in physical type and constitution. So it would be mainly the mere element of distance that makes them appear so faint and crowded thickly together into that gauzy girdle which we call the galaxy. Milky Way reveals irregularities of stellar density and star clustering on a large scale, with deep rifts between great clouds of stars. Modern photographs, particularly those of Barnard in Sagittarius, make this very apparent. Within the Milky Way, nearly in its plane and almost central, is what Eddington terms the inner stellar system, near the center of which is the Sun. Surrounding it and near its plane are the masses of star clouds which make up the Milky Way. Whether these star clouds are isolated from the inner system or continuous with it is not yet ascertained. The vast masses of the Milky Way stars are very faint, and we know nothing yet as to their proper motions, their radial motions, or their spectra. Probably a few stars as bright as the sixth magnitude are actually located in the midst of the Milky Way clusters. The fainter ninth magnitude stars certainly begin the Milky Way proper, while the stars of the 12th or 13th magnitude carry us into the very depths of the galaxy. It is now pretty generally believed that many of the dark regions of the Milky Way are due not to actual absence of stars so much as to the absorption of light by intervening tracts of nebulous matter on the hither side of the galactic aggregations, and probably in fact within the oblate inner stellar system itself. Easton has made many hundred counts of stars in galactic regions of Cygnus and Aquila, where the range of intensity of light is very marked. In fact, the star density of the bright patches of the galaxy is so far in excess of the density adjacent and just outside the Milky Way that the conclusion is inevitable that this excess is due to the star clouds. Of the distance of the Milky Way, we have very little knowledge. It is certainly not less than 1000 parsecs and more likely 5000 parsecs, a distance over which light would travel in about 16,000 years. Quite certainly, all parts of the galaxy are not at the same distance, and probably there are branches in some regions that lie behind one another. While the general regions of the nebulae are remote from the galactic plane, the large irregular nebulae as the Trifid, the Keyhole, and the Omega nebulae are found chiefly in the Milky Way. In addition to the irregular nebulae, many types of stellar objects appear to be strongly condensed toward the Milky Way, but this may be due to the inner stellar system rather than a real relation to the galactic formation. Quite different are the Magellanic Clouds, which contain many gaseous nebulae and are unique objects of the sky, having no resemblance to the true spiral nebulae, which, as a rule, avoid the galactic regions. Worthy of note also is the theory of Easton that the Milky Way has itself the form of a double branched spiral, which explains the visible features quite well, but is incapable of either disproof or verification. The central nucleus he locates in the rich galactic region of Cygnus, with the Sun well outside the nucleus itself. By combining the available photographs of the galaxy, he has produced a chart which indicates in a general way how the stellar aggregations might all be arrayed so as to give the effect of the galaxy as we see it. Shapley at Mount Wilson has studied the structure of the galactic system, in which he has been aided by Mrs. Shapley. An interesting part of this work relates to the distribution of the spiral nebulae and to certain properties of their systematic recessional motion, suggesting that the entire galactic system may be rapidly moving through space. Apparently, the spiral nebulae are not distant stellar organizations or island universes, but truly nebular structures of vast volume which in general are actively repelled from the stellar system. A tentative cosmogonic hypothesis has been formulated to account for the motions, distribution, and observed structure of clusters and spiral nebulae. An additional great problem of the galaxy is a purely dynamical one. Doubtless, it is in some sort of equilibrium, according to Eddington, that is to say, the individual stars do not oscillate to and fro across the stellar system in a period of 300 million years, but remain concentrated in clusters as at present. Poincare has considered the entire Milky Way as in stately rotation, and on the assumption that the total mass of the inner stellar system is 1000 million times the Sun's mass, and that the distance of the Milky Way is 2000 parsecs, the angular velocity for equilibrium comes out 0.5 radians per century. That is to say, a complete revolution would take place in about 250 million years. End of chapter 57.
Chapter 58 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Raven Green. Astronomy, the Science of the Heavenly Bodies, by David Todd. Star Clouds and Nebulae. From star clusters to nebulae. Only a century ago, the transition was thought to be easy and immediate. Accuracy in determining the distances of stars was just beginning to be reached. The clusters were obviously of all degrees of closeness, following to the verge of irresolvability, and it was but natural to jump to the conclusion that the mystery of the nebulae consisted in nothing but their vaster distance than that of clusters. And it was believed that all nebulae would prove resolvable into stars whenever telescopes of sufficiently great power could be constructed. But the development of the spectroscope soon showed the error of this hypothesis by revealing bright lines in the nebular spectra, showing that many nebulae emit light that comes from glowing incandescent gas, not from an infinitude of small stars. In pre-telescope days, nothing was known about the nebulae. The Great Nebula in Andromeda, and possibly the Great Nebula in Orion, are alone visible to the naked eye. But as thus seen, they are the merest wisps of light, the same as the larger clusters are. Galileo, Huygens, and other early users of the telescope made observations of nebulae, but long-focused telescopes were not well adapted to this work. Simon Mayer has left us the first drawing of a nebula, the Orion Nebula, as he saw it in 1612. The vast light-gathering power of the reflectors built by Sir William Herschel first afforded glimpses of the structure of the nebulae, and if his drawings are critically compared with modern ones, no case of motion, with reference to the stars or of change in the filaments of the nebulae themselves, has been satisfactorily made out. Only very recently has the distance of a nebula been determined, and the few that have been measured seem to indicate that the nebulae are at great distances comparable with the stars. Of all celestial objects, the nebulae fill the greatest angles, so that we are forced to conclude, with regard to the actual size of the greater nebulae as they exist in space, that they far surpass all other objects in bulk. Photography invaded the realm of the nebulae in 1880, when Dr. Henry Draper secured the first photograph of the nebula of Orion. Theoretically, photography ought to help greatly in the study of the nebulae, and enable us, in the lapse of centuries, to ascertain the exact nature of the changes which must be going on. the differences of photographic processes, of plates, of exposure, and development produce in the finished photograph vastly greater differences than any actual changes that might be going on, so that we must rely rather on optical drawings made with the telescope, or on drawings made by expert artists from photographs with many lengths of exposure on the same object. The great work on nebulae and star clusters, recently concluded by Bigordan of the Paris Observatory, and published in 5 volumes, received the award of the gold medal of the Royal Astronomical Society. While d'Arrest measured about 2,000 nebulae, and Sir John Herschel about double that number in both hemispheres, Bigordan has measured about 7,000. His work forms an invaluable lexicon of information concerning the nebulae. Classification of the nebulae is not very satisfactory if made by their shapes alone. There are perhaps 15,000 nebulae in all that have been catalogued, described, and photographed. Dreyer's New General Catalogue, NGC, is the best and most useful. Many of the nebulae, especially the large ones, can only be classified as irregular nebulae. The Orion Nebula is the principal one of this class, revealing an enormous amount of complicated detail with exceptional brilliancy of many regions and filaments. An extraordinary multiple star, Theta Orionis, occupies a very prominent position in the nebula, and photographs by Pickering have brought to light the curved filaments, very faint and optically invisible, in the outlying regions which give the Orion Nebula, in part, a spiral character. But the delicate optical wisps of this nebula are well seen, even in very small telescopes. Its spectrum yields hydrogen, helium, and nitrogen. The Orion Nebula is receding from the Earth about 11 miles in every second. Keeler and Campbell have shown that nearly every line of the nebular spectrum is a counterpart of a prominent dark line in the spectrum of the brighter stars of the constellation of Orion. A recent investigator of the distribution of luminosity in the great nebula of Orion finds that radiations from nebulium are confined chiefly to the Huygenian region of the nebula and its immediate neighborhood. Photography has revealed another extraordinary nebula or group of nebulae surrounding the stars in the Pleiades, which the deft manipulation of Barnard has brought to light. All the stars and the nebula are so interrelated that they are obviously bound together physically, as the common proper motion of the stars also appears to show. Also in the constellation Cygnus, Barnard has discovered very extensive nebulosities of a delicate, filmy, cloud-like nature, which are wholly invisible with telescopes, but very obvious on highly sensitive plates with long exposures. Another class of these objects are the annular and elliptic nebulae, which are not very abundant. The southern constellation Grus, the Crane, contains a fine one, but by far the best example is in the constellation Lyra. It is a near-perfect ring, elliptic in figure, exceedingly faint in small telescopes, but large instruments reveal many stars within the annulus. One near the center, which, although very faint to the eye, is always an easy object on the photographic plate because it is rich in blue and violet rays. The parallax of the ring nebula in Lyra comes out only 1/6 of that of the planetary nebulae, and the least greatest diameters of this huge continuous ring are 250 and 330 times the orbit of Neptune. Planetary nebulae and nebulous stars are yet another class of nebulae, for the most part faint and small, resembling in some measure a planetary disk or a star with a nebulous outline. Practically all are gaseous in composition and have large radial velocities. Probably they are located within our own stellar system. The parallaxes of several of them have been measured by Van Manen. One of the very small angle 0.023 inches, which enables us to calculate the diameter of this faint but interesting object as equal to 19 times the orbit of Neptune. End of chapter 58.
Chapter 59 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Trek. Astronomy, the Science of the Heavenly Bodies by David Todd. The Spiral Nebulae. Last and most important of all these spiral nebulae. The finest example is in the constellation Canes Venatici, and its spiral configuration was first noted by Lord Rosse, an epoch-making discovery. The convolutions of its spiral are filled with numerous star-like condensations, themselves engulfed in nebulosity. Photography possesses a vast advantage over the eye in revealing the marvelous character of this object, an inconceivably vast celestial whirlpool. Naturally, the central regions of the world would revolve most swiftly, but no comparison of drawings and photographs, separated by intervals of many years, has yet revealed even a trace of any such motion. The number of large spiral nebulae is not very great. The largest of all is the Great Nebula of Andromeda, whose length stretches over an arc of 7 times the breadth of the Moon, and its width about half as great. This nebula is a naked eye object near Eta Andromedae, and it is often mistaken for a comet. Optically, it was always a puzzle, but photographs by Roberts of England first revealed the true spiral, with ring-like formations partially distinct and knots of condensing nebulosity as of companion stars in the making. While its spectrum shows the non-gaseous constitution of this nebula, no telescope has yet resolved it into component stars. Systematic search for spiral nebulae by Keeler and later continued by Perrine at the Lick Observatory with the 36-inch Crossley reflector disclosed the existence of vast numbers of these objects, in fact many hundreds of thousands by estimation, so that next to the stars the spiral nebulae are by far the most abundant of all the objects in the sky. They present every phase according to the angle of their plane with the line of sight, and the convolutions of the open ones are very perfectly marked. Many are filled with stars in all degrees of condensation, and the appearance is strongly as if stars are here, caught in every step of the process of making. The vast multitude of the spiral nebulae indicates clearly their importance in the theory of the cosmogony, or science of the development of the material universe. Curtis of the Lick Observatory has lately extended the estimated number of these objects to 700,000. He has also photographed with the Crossley reflector many nebulae with lanes or dark streaks crossing them longitudinally through or near the center. These remarkable streaks appear as if due to opaque matter between us and the luminous matter of the nebula beyond. Perhaps a dark ring of absorptive or occulting matter encircles the nebula in nearly the same plane with the luminous worlds. Duncan has employed the 60-inch Mount Wilson reflector in photographing bright nebulae and star clusters in the very interesting regions of Sagittarius. One of these shows unmistakable dark rifts or lanes in all parts of the nebula, resembling the dark regions of the neighboring Milky Way. Pease of Mount Wilson has recently employed the 60-inch and the 100-inch reflectors of the Mount Wilson Observatory to good advantage in photographing several hundred of the fainter nebulae. Many of these are spirals, and others present very intricate and irregular forms. A search was made for additional spirals among the smaller nebulae along the galaxy, but without success. Several of the supposedly variable nebulae are found to be unchanging. Many nights in each month when the moon is absent are devoted to a systematic survey of the smaller nebulae and their spectra by photography. The visible spiral figure of all these objects is a double-branched curve, its two arms joining on the nucleus in opposing points and coiling round in the same geometrical direction. The spiral nebulae, as to their distribution, are remote from the galaxy, and the north galactic polar region contains a greater aggregation than the south. The distances of the spiral nebulae are exceedingly great. They lie far beyond the planetary and irregular gaseous nebulae like that of Orion, which are closely related to the stars forming part of our own system. Possibly, the spiral nebulae are exterior or separate island universes. If so, they must be inconceivably vast in size and would develop not into solar systems but into stellar clusters. The enormous radial velocities of the spiral nebulae averaging 300 to 400 kilometers per second or 20-fold that of the stars tend to sustain the view that they may be island universes, each comparable in extent with the universe of stars to which our sun belongs. Recent spectroscopic observations of the nebulae applying the principle of Doppler have revealed high velocities of rotation. Slipher of the Lowell Observatory made the first discovery of this sort, and Van Manen of Mount Wilson has detected in the Great Ursa Major spiral, number 101 in Messier's catalogue, a speed of rotation at 5 minutes of arc from the center that would correspond to a complete period in 85,000 years. As was to be expected, the nebula does not rotate as a rigid body, but the nearer the center, the greater the angular velocity. And Van Manen finds evidence of motion along the arms and away from the center. These great velocities appear to belong to the spiral nebulae as a class and not to other nebulae. 13 nebulae investigated by Keeler are as a whole almost at rest relatively to our system, as are the large irregular objects in Orion and the Trifid Nebula. This would seem to indicate that the spiral nebulae form systems outside our own and independent of it. Quite different from the spirals in their distribution through space are the planetary nebulae. The spirals follow the early general law of nebulae arrangement, that is, they are concentrated toward the poles of the galaxy, but the planetary nebulae, on the other hand, are very few near the poles and show a marked frequency toward the galactic plane. Campbell and Murray have found in spectroscopic evidence of internal rotatory motion in a large proportion of the planetary nebulae. The distribution of the nebulae throughout space, like that of the stars, is still under critical investigation, but the location of vast numbers of the more compact nebulae on the celestial sphere is very extraordinary. The Milky Way appears to be the determining plane in both cases. The nearer we approach it, the more numerous the stars become, whereas this is the general region of fewest nebulae, and they increase in number outward in both directions from the galaxy and toward both poles of the galactic circle. Obviously, this relation or contrarrelation of stars and nebulae on such a vast scale is not accidental, and it also must be duly accounted for in the true theory of the cosmogony. The nebulae which are found principally in and near the Milky Way are the large irregular nebulae, and vast nebulous backgrounds like those photographed by Bernard in Scorpio, Taurus, and elsewhere as well as the Keyhole, Omega, and Trifid nebulae. Allied to these backgrounds are doubtless some of the dark galactic spaces, radiating little or no intrinsic light and absorbing the light of the fainter stars beyond them. A peculiar veiled or tinted appearance has been remarked in some cases visually, and examination of the photographs strongly confirms the existence of absorbing nebulosity. The spiral nebulae are so abundant and so much attention is now being given to them, both by observers and mathematicians, that their precise relation to the stellar systems must soon be known. That is, whether they are comparatively small objects belonging to the stellar system, or independent systems on the borders of the stellar system, or, as seems more likely, vast and exceedingly remote galaxies comparable with that of the Milky Way itself. Our knowledge of the motions of the spirals, both radial and angular, is increasing rapidly and must soon permit accurate general conclusions to be drawn. End of chapter 59.
Chapter 60 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Astronomy, the Science of the Heavenly Bodies, by David Todd. Cosmogony. Down to the middle of the last century and later, it was commonly believed that in the beginning the cosmos came into being by divine fiat substantially as it is. Previously the earth had been without form and void, as in the Scripture. Had it not been for the growth and gradual acceptance of the doctrine of evolution, and its reactionary effect upon human thought, it is conceivable that the early view might have persisted to the present day. But now it is universally held that everything in the heavens above and the earth beneath is subject more or less to secular change, and is the result of an orderly development throughout indefinite past ages, a progressive evolution which will continue through indefinite eons of the future. In the writings of the Greek philosophers, and down through the Middle Ages, we find the idea of an original chaos prevailing, with no indication whatever of the modern view of the process by which the cosmos came to be what they saw it and as it is today. If we go still farther back, there is no glimmer of any ideas that will bear investigation by scientific method, however interesting they may be as purely philosophical conceptions. Many ancient philosophers, among them Anaxagoras, Democritus, and Anaximenes, regard the earth as the product of diffused matter in a state of the original chaos having fallen together haphazard, and they even presume to predict its future career and ultimate destiny. In Anaximander and Anaximenes alone do we find any conception of possible progress. Their thought was that as the world had taken time to become what it is, so in time it would pass, and as the entire universe had undergone alternate renewal and destruction in the past, that would be its history in the future. Aristotle, Ptolemy, and others appear to have held the curious notion that although everything terrestrial is evanescent, nevertheless the cosmos beyond the orbit of the moon is imperishable and eternal. By tracing the history of the intellectual development of Europe, we may find why it was that scientific speculation on the cosmogony was delayed until the 18th century, and then undertaken quite independently by three philosophers in three different countries. Swedenborg, the theologian, set down in due form many of the principles that underlie the modern nebular hypothesis. Thomas Wright of Durham, whose early theory of the arrangement of stars in the galaxy we have already mentioned, speculated also on the origin and development of the universe, and his writings were known to Kant, who is now regarded as the author of the modern nebular hypothesis. This presents a definite mechanical explanation of the development and formation of the heavenly bodies, and in particular those composing the solar system. Kant was illustrious as a metaphysician, but he was a great physicist or natural philosopher as well, and he set down his ideas regarding the cosmogony with precision. Learned in the philosophy of the ancients, he did not follow their speculative conceptions, but merely assumed that all the materials from which the bodies of the solar system have been fashioned were resolved into their original elements at the beginning, and filled all that part of space in which they now move. True, this is pretty near the chaos of the Greeks, but Kant knew of the operation of the Newtonian law of gravitation, which the Greeks did not. As a natural result of gravitative processes, Kant inferred that the denser portions of the original mass would draw upon themselves the less dense portions. Whirling motions would be everywhere set up, and the process would continue until many spherical bodies, each with a gaseous exterior in process of condensation, had taken the place of the original elements which filled space. In this manner Kant would explain the sameness and direction of motion, both orbital and axial, of all the planets and satellites of our system. But many philosophers are of the opinion that Kant's hypothesis would result, not in the formation of such a collection of bodies as the solar system is, but rather in a single central sun formed by common gravitation toward a single center. From quite another viewpoint, the work of the elder Herschel is important here. No one knew the nebulae from actual observation better than he did, but, while his ideas about their composition were wrong, he nevertheless conceived of them as gradually condensing into stars or clusters of stars. And it was this speculative aspect of the nebulae, not as a possible means of accounting for the birth and development of the solar system, which constitutes Herschel's chief contribution to the nebular hypothesis. Classifying the nebulae, which he had carefully studied with his great telescopes, it seemed obvious to him that they were actually in all the different stages of condensation, and subsequent research has strongly tended to substantiate the Herschelian view. Then came Laplace, who took up the great hypothesis where Kant and Herschel had left it, added new and important conceptions in the light of his mature labors as mathematician and astronomer, and put the theory in definitive form, such that it has ever since been known under the name of Laplacian nebular hypothesis. For reasons like those that prevailed with Kant, he began the evolution of the solar system with the sun already formed as the center, but surrounded by a vast incandescent atmosphere that filled all the space which the sun's family of planets now occupy. This entire mass, sun, atmosphere, and all, he conceived to have a stately rotation about its axis. With rotation of the mass and slow reduction of temperature in its outer regions, there would be contraction toward the solar center, and an increase in velocity of rotation until the whole mass had been much reduced in diameter at its poles and proportionally expanded at its equator. When the centrifugal force of the outer equatorial masses finally became equal to the gravitational forces of the central mass, then these conjoined outer portions would be left behind as a ring, still revolving at the velocity it had acquired when detached. The revolution of the entire inner mass goes on, its velocity accelerating until a similar equilibration of forces is again reached, when a second rotating ping is left behind. Laplace conceived the process as repeated until as many rings had been detached as there are individual planets, all central about the sun, or nearly so. In all, then, we should have non-gaseous rings, the outer ones preceding the inner in formation, but not all existing as rings at the same time. Radiation from the ring on all sides would lead to rapid contraction of its mass, so that many nuclei of condensation would form, of various sizes, all revolving round the central sun in practically the same period. Laplace conceived of the evolution of the ring to proceed still farther till the largest aggregation in it had drawn to itself all the other separate nuclei in the ring. This, then, was the planet in embryo, an effective diminutive sum, a secondary incandescent mass, endowed with axial rotation in the same direction as the parent nebula. With reduction of temperature by radiation, polar contraction and equatorial expansion go on, and planetary rings are detached from this secondary mass in exactly the same way as from the original Sun nebula. And these planetary rings are, in the Laplacian hypothesis, the embryo moons or planetary satellites, all revolving round their several planets in the same direction that the planets revolve about the sun. In the case of one of the planetary rings, its formation was so nearly homogeneous throughout that no aggregation into a single satellite was possible. All portions of the ring being of equal density, there was no denser region to attract the less dense regions, and in this manner the rings of Saturn were formed, in lieu of condensation into a separate satellite. Similarly, in the case of the primal solar ring that was detached next after the Jovian ring, there was such a nice balancing of masses and densities that, instead of a single major planet, we have the well-known asteroidal ring, composed of innumerable discrete minor planets. This, then, in bare outline, is the Laplacian nebular hypothesis, and it accounted very well for the solar system as known in his day. The fairly regular progression of planetary distances, their orbits round the sun all nearly circular and approximately in a single plane, the planetary and satellite revolutions in orbit all in the same direction, the axial rotations of planets in the same direction as their orbital revolutions, and the plane of orbital revolution of the satellites practically coinciding with the plane of the planet's axial rotation. But the principle of conservation of energy was, of course, unknown to Laplace, nor had the mechanical equivalence of heat with other forms of energy been established in his day. In 1870, Lane of Washington first demonstrated the remarkable law that a gaseous sphere, in process of losing heat by radiation and contraction because of its own gravity, actually grows hotter instead of cooler, as long as it continues to be gaseous and not liquid or solid. So there is no need of postulating with Laplace an excessively high temperature of the original nebula. The chief objection to Laplace's hypothesis by modern theorists is that the detachment of rings, though possible, would likely be a rare occurrence. Protuberances or lumps on the equatorial exterior of a swiftly revolving mass would be more likely, and it is much easier to see how such masses would ultimately become planets than it is to follow the disruption of a possible ring and the necessary steps of the process by which it would condense into a final planet. The continued progress of research in many departments of astronomy has had an important bearing on the nebular hypothesis, and we may rest assured that this hypothesis, in somewhat modified form, can hardly fail of ultimate acceptance, though not in every essential as its great originator left it. Lord Rosse's discovery of spiral nebulae, followed up by Keeler's photographic search for these bodies, revealing their actual existence in the heavens by the hundreds of thousands, has led to another criticism of the Laplacian theory. Could Laplace have known of the existence of these objects in such vast numbers, his hypothesis would no doubt have been suitably modified to account for their formation and development. It is generally considered that the ring of Saturn suggested to Laplace the ring feature in his scheme of origin of planets and satellites. So far as we know, the Saturnian ring is unique, the only object of its kind in the heavens. Whereas, next to the star itself, the spiral nebula is the type object which occurs most frequently. A theory, therefore, which will satisfactorily account for the origin and development of spiral nebulae must command recognition as of great importance in the cosmogony. Such a theory has been set forth by Chamberlain and Moulton in their planetesimal hypothesis, according to which the genesis of spiral nebulae happens when two giant suns approach each other so closely that tide-producing effects take place on a vast scale. These suns need not be luminous. They may perhaps belong to the class of darker extinguished suns. The evidences of the existence of such in vast numbers throughout the universe is thought to be well established. Now, on close approach, what happens? There will be huge tides, and the nearer the bodies come to each other, the vaster the scale on which tides will be formed. If the bodies are liquid or gaseous, they will be distorted by the force of gravitation, and the figure of both bodies will become ellipsoidal. And at last, under greater stress, the restraining shell of both bodies will burst asunder on opposite sides in streams of matter from the interior. In this manner the arms of the spiral are formed. As Chamberlain puts it, if, with these potent forces thus nearly balanced, the sun closely approaches another sun, or body of like magnitude, the gravity which restrains this enormous elastic power will be reduced along the line of mutual attraction. At the same time, the pressure transverse to this line of relief will be increased. Such localized relief and intensified pressure must bring into action corresponding portions of the sun's elastic potency, resulting in protuberances of corresponding mass and high velocity. Only a fraction of 1% of the sun's mass ejected in this fashion would be sufficient to generate the entire planetary system. Nuclei or knots in the arms of the spiral gradually grew by accretion, the four interior knots forming Mercury, Venus, the Earth, and Mars. The Earth knot was a double one, which developed into the Earth-Moon system. The absence of a dominating nucleus beyond Mars accounts for the zone of the asteroids remaining in some sense in the original planetesimal condition. The vaster nuclei beyond Mars gradually condensed into Jupiter, Saturn, Uranus, and Neptune, and lesser nuclei related to the larger ones form the systems of moons or satellites. The orbits of the planetesimals and the planetary and satellite nuclei would be very eccentric, forming a confusion of ellipses with frequently crossing paths. Collisions would occur, and the nuclei would inevitably grow by accretion. Each planet, then, would clear out the planetesimals of its zone, and Moulton shows that this process would give rise to axial revolution of the planet in the same direction as its orbital revolution. The eccentricities would finally disappear, and the entire mass would revolve in a nearly circular orbit. Rotation twists the streams into the spiral form, and the huge amounts of wreckage from the near collision are thrown into eddies. The fragments or particles, planetesimals, which have given the name to the theory, begin their motion round their central sun in elliptical paths as required by gravitation. The form of the spiral is preserved by the orbital motion of its particles. There is a gradual gathering together of the planetesimals at points or nodes of intersection, and these become aggregations of matter, nuclei that will perhaps become planets, though more likely other stars. The appulse or near approach is but one of the methods by which the spiral nebulae may have come into existence. The planetesimal hypothesis would seem to account for the formation of many of these objects as we see them in the sky, though perhaps it is hardly competent to replace entirely the Laplacian hypothesis of the formation of the solar system, which would appear to be a special case by itself. It will be observed that while the Laplacian hypothesis is concerned in the main with the progressive development of the solar system and systems of a like order surrounding other stellar centers, whose existence is highly probable, the origin and development of the stellar universe is a vaster problem which can only be undertaken and completed in its broadest bearings when the structure of the stellar universe has been ascertained. Darwin's important investigations in 1877 to 1878 on tidal friction may be here related. Before his day, acceptance of the ring theory of development of the moon from the earth had scarcely been questioned, but his recondite mathematical researches on the tidal reaction between a central yielding mass and a body revolving round it brought to light the unsuspected effect of tides raised upon both bodies by their mutual attraction. The types of tides here meant is not the usual rise and fall of the waters of the ocean, but primeval tides in the plastic material of which the earth in its early history was composed. The Newtonian law of gravitation afforded a complete explanation of the rise and fall of the waters of the oceans, but as applied to the motions of planets and satellites by the Lagrangian formulae, it presupposed that all these bodies are rigid and unyielding. However, mutual tides of phenomenal height in their early plastic substances must have been a necessary consequence of the action of the Newtonian law, and they gradually drew upon the Earth's rotational moment of momentum. In its very early history, before there was any moon to produce tides, the Earth rotated much more rapidly, that is, the day was very much shorter than now, probably about 5 or 6 hours long. And with the rapid whirling, it was not a Laplacian ring that was detached, but a huge globular mass was separated from the plastic Earth's equator. Darwin shows that the gravitative interaction of the two bodies immediately began to raise tides of extraordinary height in both, therefore tending to slow down the rotational periods of both bodies. Action and reaction being equal, the reaction at once began driving the moon away from the Earth and thereby lengthening its period of revolution. So small was the mass of the moon and so near was it to the Earth that its relative rotational energy was in time completely used up, and the moon has ever since turned her constant face toward us. Tides of sun and moon in the plastic Earth, acting through the ages, slowed down the Earth's rotation to its present period, or the length of the day. Moulton, however, has investigated the tidal theory of the origin of the moon in the light of the planetesimal hypothesis, concluding that the moon was never part of the Earth and separated therefrom by too rapid rotation of the Earth, but that the distance of the two bodies has always been the same as now. The more massive Earth has in its development throughout time robbed of the less massive moon in the gradual process of accretion. So the moon has never acquired either an ocean or atmosphere, and this view is acceptable to geologists who have studied the sheer lunar surface, Shaler of Harvard among the first, and laid the foundations for a separate science of selenology. Tidal friction has also been operant in producing sun-raised tides upon the early plastic substances which compose the planets, more powerfully in the case of planets nearer the sun, less rapidly if the planet's mass is large, also less completely if the planet has solidified earlier on account of its small dimensions. So Darwin would account for the present rotation periods of all the planets. Both Mercury and Venus powerfully acted on by the sun on account of their nearness to him, and their rotational energy completely exhausted, so that they now and for all time turn a constant face toward him, as the moon does to the Earth, and possibly Mars even yet undergoing a very slight lengthening of their day. Jupiter and Saturn, also Uranus and probably Neptune, still exhibiting relatively swift axial rotation because of their great mass and great original moment of momentum, and also by reason of their vast distances from the central tide-raising body, the Sun. By applying to stellar systems principles developed by Darwin, C accounted for the fact, to which he was the first to direct attention, that the great eccentricity of the binary orbits is a necessary result of the secular action of tidal friction. The double stars, then, were double nebulae, originally single, but separated by a process allied to that known as fission in protozoans. Indeed, Poincaré proved mathematically that a swiftly revolving nebula, in consequence of contraction, first undergoes distortion into a pear-shaped or hourglass figure, the two masses ultimately separating entirely, and the observations of the Herschels, Lord Rosse, and others, with the recent photographic plates at the Lick and Mount Wilson observatories, afford immediate confirmation in a multitude of double nebulae widely scattered throughout the nebular regions of the heavens. Jeans of Cambridge, England, among the most recent of mathematical investigators of the cosmogony, balances the advantages and disadvantages of the differing cosmogonic systems as follows in his Problems of Cosmogony and Stellar Dynamics. Some hundreds of millions of years ago, all the stars within our galactic universe formed a single mass of excessively tenuous gas in slow rotation. As imagined by Laplace, this mass contracted owing to loss of energy by radiation, and so increased its angular velocity until it assumed a lenticular shape. After this, further contraction was a sheer mathematical impossibility, and the system had to expand. The mechanism of expansion was provided by matter being thrown off from the sharp edge of the lenticular figure, the lenticular center now forming the nucleus, and the thrown-off matter forming the arms of a spiral nebula of the normal type. The long filaments of matter which constituted the arms, being gravitationally unstable, first formed into chains of condensation about nuclei, and ultimately formed detached masses of gas. With continued shrinkage, the temperature of these masses increased until they attained to incandescence and shone as luminous stars. At the same time, their velocity of rotation increased until a large proportion of them broke up by fission into binary systems. The majority of the stars broke away from their neighbors and so formed a cluster of irregularly moving stars, our present galactic universe, in which the flattened shape of the original nebula may still be traced in the concentration about the galactic plane, while the original motion along the nebular arms still persists in the form of star streaming. In some cases, a pair or small group of stars fail to get clear of one another's gravitational attractions and remain describing orbits about one another as wide binaries or multiple stars. The stars which were formed last, the present B-type stars, have been unusually immune from disturbance by their neighbors, partly because they were born when adjacent stars had almost ceased to interfere with one another, partly because their exceptionally large mass minimized the effect of such interference as may have occurred. Consequently, they remain moving in the plane in which they were formed, many of them still constituting closely associated groups of stars, the moving star clusters. At intervals it must have happened that two stars passed relatively near to one another in their motion through the universe. We conjecture that something like 300 million years ago our Sun experienced an encounter of this kind, a large star passing within a distance of about the Sun's diameter from its surface. The effect of this, as we have seen, would be the ejection of a stream of gas toward the passing star. At this epoch the Sun is supposed to have been dark and cold, its density being so low that its radius was perhaps comparable with the present radius of Neptune's orbit. The ejected stream of matter, becoming still colder by radiation, may have condensed into liquid near its ends, and perhaps partially also near its middle. Such a jet of matter would be longitudinally unstable, and would condense into detached nuclei, which would ultimately form planets. End of chapter 60.
Chapter 61 of Astronomy, the Science of the Heavenly Bodies. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Read by Andy Glover. Astronomy, the Science of the Heavenly Bodies, by David Todd. Cosmogony in Transition. We have seen how Wright in 1750 initiated a theory of evolution, not only of the solar system, but of all the stars and nebulae as well. How Kant in 1752, by elaborating this theory, sought to develop the details of evolution of the solar system on the basis of the Newtonian law, though weakened, as we know, by serious errors in applying physical laws. How Laplace in 1796 put forward his nebular hypothesis of origin and development of the solar system by contraction from an original gaseous nebula in accord with the Newtonian law. How Sir William Herschel in 1810 saw in all nebulae merely the stuff that stars are made of. How Lord Rosse in 1845 discovered spiral nebulae. How Helmholtz in 1854 put forward his contraction theory of maintenance of the solar heat, seemingly reinforcing the Laplacian theory. How Lane in 1870 proved that a contracting gaseous star might rise in temperature. How Roche in 1873, in attempting to modify the Laplacian hypothesis, pointed out the conditions under which a satellite would be broken up by tidal strains. How Darwin in 1879 showed that the theory of tidal evolution of non-rigid bodies might account for the formation of the moon, and binary stars might originate by fission. How Keeler in 1900 discovered the vast numbers of spiral nebulae. How Chamberlain and Moulton in 1903 put forward the planetesimal hypothesis of formation of the spiral nebulae, showing also how that hypothesis might account for the evolution of the solar system. And how Jeans in 1916 advocated the median ground in evolution of the arms of the spiral nebulae, showing that they will break up into nuclei if sufficiently massive. In all these theories, truth and error, or lack of complete knowledge, appear to be intermingled in varying proportions. Is it not early yet to say either that any one of them must be abandoned as totally wrong, or on the other hand, that any one of them, or indeed any single hypothesis, can explain all the evolutionary processes of the universe? Clearly, the great problems cannot all be solved by the kinetic theory of gases and the law of gravitation alone. Recent physical researches into subatomic energy and the structure and properties of matter appear to point in the direction where we must next look for more light on such questions as the origin and maintenance of the sun's heat, the complex phenomena of variable stars, and the progressive evolution of the myriad bodies of the stellar universe. Because we have actually seen one star turn into a nebula, we should not jump to the conclusion that all nebulae are formed from stars, even if this might seem a direct inference from the high radial velocities of planetary nebulae. Quite as obviously, many of the spiral nebulae are in a stage of transition into local universes of stars. Even more obvious from the marvelous photographs in our day than the evolution of stars from nebulae of all types was to Herschel in his day. The physicist must further investigate such questions as the building up of heavy atomic elements by gravitative condensation of such lighter ones as compose the nebulae. And laboratory investigation must elucidate further the process of development of energy from atomic disintegration under very high pressures. This leads to a reclassification of the stars on a temperature basis. Equally important is the inquiry into the mechanism of radiative equilibrium in sun and stars. Not impossibly, the process of the Earth's upper atmosphere in maintaining a terrestrial equilibrium may afford some clue. What this physical mechanism may be is very incompletely known, but it is now open to further research through recent progress of aeronautics, which will afford the investigator a ceiling of 50,000 feet and probably more. Beneath this level, perhaps even below 40,000 feet, lie all the strata, including the inversion layer, where the sun's heat is conserved and an equilibrium maintained. Even 10 years ago, had an astronomer been asked about the physical condition of the interior of the stars, he would have replied that information of this character could only be had on visiting the stars themselves, and perhaps not even then. But at the Cardiff meeting of the British Association in 1920, Eddington, the president of Section A, delivered an address on the internal constitution of the stars. He cites the recent investigations of Russell and others on truly gaseous stars, like Aldebaran, Arcturus, Antares, and Canopus, which are in a diffuse state and are the most powerful light givers, and thus are to be distinguished from the denser stars like our Sun. The term giants is applied to the former, and dwarfs to the latter, in accord with Russell's theory. As density increases through contraction, these terms represent the progressive stages from earlier to later in the star's history. A red or M-type star begins its history as a giant of comparatively low temperature. Contracting, according to Lane's law, its temperature must rise until its density becomes such that it no longer behaves as a perfect gas. Much depends on the star's mass, but after its maximum temperature is attained, the star, which has shrunk to the proportions of a dwarf, goes on cooling and contracts still further. Each temperature level is reached and passed twice, once during the ascending stage and once again in descending, once as a giant and once as a dwarf. Thus there are vast differences in luminosity. The huge giant, having a far larger surface than the shrunken dwarf, radiates an amount of light correspondingly greater. The physicist recognizes heat in two forms: the energy of motion of material atoms and the energy of ether waves. In hot bodies with which we are familiar, the second form is quite insignificant, but in the giant stars, the two forms are present in about equal proportions. The superheated conditions of the interior of the stars can only be estimated in millions of degrees, and the problem is not one of convection currents, as formerly thought, bringing hot masses to the surface from the highly heated interior. But how can the heat of the interior be barred against leakage and reduced to the relatively small radiation emitted by the stars? Smaller stars have to manufacture the radiant heat which they emit, living from hand to mouth. The giant stars merely leak radiant heat from their store. So a radioactive type of equilibrium must be established, rather than a convective one. Laboratory investigations of the very short waves are now in progress, bearing on the transparency of stellar material to the radiation traversing it, and the penetrating power of the star's radiation is much like that of X-rays. The opacity is remarkably high, explaining why the star is so nearly heat-tight. Opacity being constant, the total radiation of a giant star depends on its mass only, and is quite independent of its temperature or state of diffuseness, so that the total radiation of a star, which is measured roughly by its luminosity, may readily remain constant during the entire giant stage of its history. As Russell originally pointed out, giant stars of every spectral type have nearly the same luminosity. From the range of luminosity of the giant stars, then, we may infer their range of masses. They come out much alike, agreeing well with results obtained by double star investigation. These studies of radiation and internal condition of the stars again bring up the question of the original source of that supply of radiant energy, continually squandered by all self-luminous bodies. The giant stars are especially prodigal, and radiate at least 100-fold faster than the sun. A star is drawing on some vast reservoir of energy, says Eddington, by means unknown to us. This reservoir can scarcely be other than the subatomic energy which, it is known, exists abundantly in all matter. We sometimes dream that man will one day learn how to release it and use it for his service. The store is well nigh inexhaustible. If only it could be tapped. There is sufficient in the sun to maintain its output of heat for 15 billion years. End of chapter 61. End of Astronomy, the Science of the Heavenly Bodies, by David Todd.